Okay, so we should be all set now. We have a Zoom link. We've shared our screen. They should be able to hear us. Once you guys tell me that the online people are set, we will start. Who said my friend is online? Oh, yeah. Just let me know when they're ready and I will start. Okay. By the way, while we're waiting for them, how far along are you guys in deploying the products for your directed research? Did you guys get to test it on a reasonable scale? I know some of the groups have done it, but which groups are, let's say, within the next 6 months are going to have a product ready for deployment?
In our case, our project is already finished for step 2. We need just the final step, but we still haven't started with our client.
Okay, okay. But push it. So generally what you would notice is that deploy this as a redundant component in your hierarchy, in your organizational setup, and you will see that you will start collecting information about weaknesses of this, which you can fill. So don't put it as like a critical component yet, because of course it would not be ready. But with time, you can collect information about, and of course we will help you if there is something that we can help with. Just let us know. We'll help you and we will guide you through the process toward deployment. Okay. How did you guys do with the assessment, the employee assessment thing?
Yeah, we almost done with the application. It's still working on.
Okay, guys. So all set. Okay. So let's start. Okay. So about this course, this is basically the list of topics that we are going to cover in this course. My target is to go around this region in this first module. Okay, so essentially we will cover all the evolution of the field of NLP. Okay, where we started, how these components were developed, what are the challenges. First, we'll understand why NLP is difficult. Okay, you are toward the end of a professional master's degree. You have studied a lot of tools. As such, any machine learning AI problem should be with the tools that you have. But you will see that NLP might not be trivially easy to be handled in that way. By the way, in the back, can you guys hear me? Can you hear me? Mic testing, mic testing. Is it better? Okay. So what you would notice is that the tools, the machine learning tools, the deep learning architectures that we have studied, they would not be tailor-made for NLP applications. Okay, I'll give you some data and I'll ask you to use deep neural network, and you would see that very quickly we would start running into trouble. Okay, so we would need to have a different set of tools, deep learning tools to use for natural language processing application, and there is an evolution of it. So we start from something which we can already do, like neural networks. Then we see that it doesn't work, so we improve it to recurrent neural networks. Then we find some weaknesses in recurrent neural networks, so we go to LSTM GRUs. Then we find some weaknesses into them, and we go to attention-based methods. And attention-based methods is basically the state of the art now in AI in general, not just NLP. It's also making very good progress in computer vision applications. Okay. And rather surprisingly, it's not a very old algorithm. It's 8 years old. So the attention-based methods, well, the original algorithm is slightly old, but the transformer architecture for attention, it was introduced in a paper from Google in 2017. And within 8 years, the entire NLP field is just this one tool. Okay. In fact, if in some places, if you go through the history of the field, people say, no, just teach us the transformer and we are good. But it's good to know the history of the field because in machine learning, there is, in AI in general, there is a slightly cyclic behavior to the field. So about 2 years ago, state space models were quite common. Okay, it's just a reworked version of RNNs. So it's good to know the evolution of the field so that when there is, let's say, a trace back, people go back to one of the older tool, modify it and make it better. You don't have to start from scratch. You know how the field evolved. And it's not a very long history. I'm not going to take 8 days to give you guys the full historical evolution. So we will take about 4 days to go from the very basic to the state of the art. And then the next 4 days, we'll just work on the applications of the state of the art. Okay, everybody is with me? Okay. So next, regarding some course logistics, how are we going to grade this course? So we will have 40% homeworks, 40% project, and 20% exam. Okay. So homeworks, you'll have 2 sets of homeworks. A homework would be released at the end of this 4-day session, and then another homework would be released at the end of the next 4-day session. I'll give you ample time, about 2 weeks to complete it, but the deadline, it would come with the homework. So when we give you a homework sheet, it will have all the details of when it's due, how it's going to be graded, etc. Okay. You're going to have a course project. Okay. Typically, I expect you guys to do it in a group of 4. I got a message from a group yesterday said that we are 6 people. We might grant you an exception to mix a group of 6, but up to 4 is a very good number. Okay. So if you want to do it individually, most welcome. You want to do it in a group of 2, 3, up till 4 is fine. Okay. We'll give you some more information about that. And finally, we're going to have an exam. I haven't quite made up my mind about it. Certainly, there is going to be an MCQ component of it. Okay, I'm just going to give you a sheet and you're going to do some MCQ. I might ask you some design question as well. Okay, so this is paper-based. Okay, this part is paper-based. And there might be a small coding exam as well, where we give you a code base. I give you some code with certain, let's say, components missing, which you guys have to complete. Okay, so I will see how we progress in this course and then decide on the exact structure of the exam accordingly. Okay, but as you see, I haven't weighted it a lot because I'm aware that project is something which is mostly an outcome for me in this. So you will see that in the project space, you have lots of room to do good projects. I have a group, a list of about 100 projects from MOI transformation department, collected from MOI department. Almost all of them are NLP projects. Okay. So if you guys are short of ideas of what to do, let us know. We'll give you a good project from MOI. Okay. From it will be some use case from MOI where you can use NLP tools. Okay. Okay, so some additional logistics. So expect you guys to submit the group information by March 6th. Okay, so this is before we meet the second time, because for group you don't need to do anything, you just need to talk to a couple of friends and create a group. The project proposal is after the second session when we get together, because I would like for you guys to submit the course proposal once you have seen all the tools available. Okay. So essentially, when we have looked at applications of NLP, then you can find some applications which are of interest to you. Okay. So I've given a fair deadline, and then we have about 1 month to complete it. Okay. So toward the end of this semester, you will submit the project and we'll grade it. Okay. Any question? Is this enough time? More than enough. Okay, so now with this, we come to the actual fun part of this course, which is studying NLP. So the good thing is that you guys are not beginners in AI. You guys have been studying AI for a while. So what I'm going to do is, first, I'm going to ask you guys, what do you think NLP is? Okay. What type of applications do you think are NLP application?
The way AI try to understand natural language, basically,
Okay,
and basically understand it like a human would.
okay, so understanding language. Okay, so this is kind of like a high level abstract goal, but I'm talking more about applications. What type of applications do you think are NLP applications? Okay, summarization. Okay, translation.
Context understanding.
I'm sorry,
Context.
context understanding. Okay, context understanding. I would modify it a little and I would say question answering.
Yeah.
Okay, so understand context to answer some questions. Okay, sentiment analysis. Anything else? These are, I would say, the major applications of NLP. Okay. In fact, the one which is the most popular one these days is this one, question answering chatbot. Okay. So Perplexity, ChatGPT, Gemini, all of these are basically question answering. These are chatbots, conversational chatbots. I'm sorry? Yes. Okay.
Will transforming the language into another form of media under NLP, like text to image, text to audio?
Yeah, so we called it multimodal learning. We will cover a little bit of it. Okay, but that's where the strength of transformer comes. What allows you to collect that very different mediums of data, for example, speech, text, images, videos, and do some joint machine learning on them. We were doing it before transformers as well, but transformer provide a very unified tool to do multimodal learning, and that's what we will see. Okay. Okay. So a little bit of history, like Doa, can you call Sultan and tell him I'm in a class? Thank you. Okay, so these type of applications were basically the earlier applications of NLP. And I will explain why these were the early applications, why these were slightly easy, why these are, for example, this is a significantly tough problem to handle in NLP, and we'll explain why it is. Translation is an earlier application of NLP and so on. So let's take, for example, sentiment analysis. Okay. So sentiment analysis was important because, of course, it has its uses in marketing and in product assessment and so on. So basically, essentially, it's related to money. So it was important to get a hold of it, to have machine learning solutions which can look at reviews or feedback provided by the users and automatically provide a sentiment for it. So what's the challenge? How would it typically look? Let's say we are talking about movies. So a review can be a great movie. Okay. Or it can be great movie, or it can be abstract. Okay, sentiment analysis, by the way, is a supervised machine learning problem. Okay, so you'd have some text and you'd have some label for it. So let's say I have label. I have label, let's say 1, 0, and -1. Okay, despite the fact that we would not use it like this, but 1 is positive, 0 is neutral, -1 is negative. Okay, so all three of them are positive sentiment. And let me take another one. Bad movie. It's -1. Okay, movie. 0. So this is how your data set would look. So up till now, the bulk of machine learning that you guys have done, you have done it on images or on tables. Okay, so it's data which has some structure. Yeah. So essentially, what we are doing in machine learning is this. So you have some data. Okay, and you have some table which is in some. Okay, it can be either number or it can be from a set. Okay, so this would be a regression problem, and this would be classification. This is your data for supervised machine learning, right? This is a problem you would typically try to solve. You would be given x and y, and what you would learn is some function parameterized by theta, which takes in an x and gives you a y hat. Okay, and then you have some loss function between y and y hat. Okay. This is the entire paradigm of supervised machine learning. Okay. You have some data. Okay. You have some parameterized function parameterized by theta. Okay. You have a loss function between the output of this parameterized function and the actual label, and you want to minimize the loss. Of course, this loss is minimized with respect to theta. So you adjust theta such that y hat which is close to y. Okay, everybody's with me? Here we should be on the same page because we have been doing it for the past 1.5 years. So now the question is, why can't I do this for NLP? The problem that I just saw, sentiment analysis. So what's I know that for sentiment analysis, my y is in a set -1, 0, 1. Okay. What can you tell me about x? I'm sorry? It would be language, but when we write something, can we like map this language into some real number? For example, image. If you have an image, okay, which is 256 times 256 pixels, okay, you can map it to let's say a number between 0 and 1. Okay, so it can be in a set 0 to 1, 256 times 256. So you have 256 times 256 numbers which are between 0 and 1. Okay, so x is in this interval. So it's a fixed structure. It's a fixed array, fixed length vector, where each component is between 0 and 1. So we know how to do things on this. We can use a convolutional neural network. We can use neural networks in general. Convolutional neural networks is a special type of neural network. But what's the issue with sentiment analysis? Why can't I do this? This is what neural network based approaches.
Because of -1.
I'm sorry?
Because of -1.
No, but -1 is this is label, right? Labels you can take -1, 0, 1 and label it 0, 1, 2. Not an issue. Okay, the issue is with x. But what is the issue with x?
To map those words and the letters to numbers.
Okay.
Use it as is we can.
Okay. So in general, that's true. Like for example, images are colors, right? But we have technique to map these colors into real numbers. Tokenizer is essentially doing the same thing. It's taking words and mapping them into some characters because, of course, computer does not understand English. Computer understand numbers. Okay, operations are in numbers. So we'll be fine. But you guys took NLP course. So what's the issue? Why can't I use, sorry? I'm sorry, a bit louder, please. No, but what's the issue? I'm dealing with text, I know that. But why can't I use a neural network for text? A fixed network? The size. The issue is that image is fixed. You will get a 256 by 256 time grid, and everything wouldn't be in that. Even if an image is a different size, you can resize it. Okay, you can do simple interpolation, and you will have a fixed size grid. The problem with text is that text is not fixed length.
Paddings.
So step by step. Okay, it's not fixed length. Okay, the same sentiment you see. These three are representing the same sentiment, but the first one had 1, 2, 3, 4, 5 words. The second one had 2 words. The third one had 1 word, and you can see that it can be 10,000 words. Some people like writing. So, so sometime when we collect information from a student, there are students who write like literally 1,000 page, 1,000 word feedback. So now that's the problem. Okay, because this X, now at least for now, the tools that I have, I don't know of converting it into a fixed size feature. Okay, that's the core challenge of NLP. Okay, and by the way, in this particular class, my Y is fixed length. Okay, because my Y is 3 classes, but you might have cases where Y is also not fixed. Can you give me an example where input X is not fixed length and Y is not fixed length in NLP? So translation, for example, text generation, for example, summarization, for example, all of these are examples where the output is also not fixed length. Okay, so X lives in some D-dimensional space where D is not fixed, and Y lives in some C-dimensional space where C is not fixed. So at least as of now, I don't know of any tools to handle this. Okay, so now we'll have to come up, this course will have to come up with a set of new tools which can handle problems like this. Everybody's with me? And I'll tell you something funny. The state-of-the-art solution is actually just kind of avoiding this problem with smart engineering. Okay, because what we say is in transformers is that we say that we will just take a context length. So we will assume that the input sequence is 1,000 word and the output sequence is also 1,000. Okay, but how? There is some engineering with it and we'll come to it. But at least let's agree on the challenge. Okay, everybody's with me? So now let's look at some possible solutions for this challenge. Okay, what can we do? We have identified a challenge. Okay, let's try to see what we can do to, what can be some of the methods where we can use the tools which are available to us. Okay, so again, let's come to sentiment analysis.
For example, use known words that represent similar sentiment. If it's represented in the text, then that means it's possible, more likely than not.
Yeah.
It's good enough.
We'll come to it. Just bear with me 1 second. Okay, so sentiment analysis. So the first thing that I would suggest we think of, so you guys have seen autoencoders, right? Okay, you guys have seen autoencoders, variational autoencoders. Okay, so what do autoencoders do? Okay, so basically, essentially, you have some information and you are extracting some low dimensional feature from it, compressed feature out of this data. Okay, essentially, you can think of it as some sort of feature engineering, but learned feature engineering. So you have some data and you extract a good feature from it, which represents the entire data. Okay, so you guys are technically familiar of feature engineering. Okay, so the first solution that I would suggest we use is feature engineering. Okay, so I can have a text of any length. Okay, but I somehow extract a feature out of it, which is fixed length. Okay, so now what I want you guys to do is to tell me what can this feature be. You guys already are machine learning experts, at least on the vision part, so you should be able to tell me a few features. Okay, so let me take a step back and let me write some text, and then you tell me what would be the feature for it. So the text that I'm trying to write is, the feature that I want to generate is, it was a great movie. Now you guys have to give me a feature for it, and let me write two other ones. This is one. Great movie. It's fantastic. This is the data. I want to extract a feature which is same length for all three. And of course, it's representative of the data as well. So what would I do? Give me the most naive, simple feature. I think you were going, you were going in the right direction as well. You want to take a step at it, just go with it.
Yeah, just when there's great, it's a positive sentiment. Something like that.
No, but I'm not doing sentiment analysis yet. I'm just asking you to engineer a feature, which is fixed length.
Known word that represents something. A word label, like basically, if the word exists in the text, that represents something.
Okay. So yeah. Okay. So you had something?
Maybe a vector that would represent the count.
That's good.
Bag of words.
Okay. So all of you, what you're saying is these are bag of word techniques, which is basically just count frequency of words. Okay. What our friend here is saying is just take some important words. Okay. Like words which represent positive and negative sentiments, and just look at those. So essentially what we will do is we'll have a vector where we're just looking at frequency of certain words. So words like great, fantastic, bad,
Equal.
whatever. Okay. And we'll go to each sentence and we'll just count their frequency, see if these words are present or not. These are called bag of words because they don't look at order of the words. Okay, they just look at which words are present in them. Okay. So essentially, I would see if great is present once, I'll put 1 here. If great is present twice, I'll put 2 here. If great is present 3 times, I'll put 3 here. It's same on with fantastic and so on and so on. Okay. So this is what I would call a naive approach of feature engineering. Okay. A complete version of this is, rather than looking at some important words, I just look at all the words in the dictionary. So I look at my data and I see which words are present in it. Okay. I create a long vector for them. Okay. So let's say in my data set, in movie review data set, there is, let's say 10,000 unique words. So I'll have a vector of size 10,000. And then I just put frequency of each word in there. So now I have taken a problem where input was variable length to a problem where input is fixed length. This problem now you can learn things from it. You create these vectors, you have engineered these features. You take these features, you feed it into a neural network, and you can learn things. Okay, everybody's with me? So now you guys in this class so far have identified a challenge with machine learning approaches, and you have found a solution for it. Okay. Now, what's the issue with this approach? It's a valid approach, it would work. Okay, now we are coming toward what are the potential weaknesses of this approach. So what are the weaknesses?
False positives. Wouldn't represent context.
Okay, so the first one is that because it's a bag of words, it does not capture context completely. I'll give you an example. So if I have a sentence, good movie.
Not as good as the previous one.
I'll give you a better example. Good movie, not bad. Okay, and bad movie,
Okay.
not good. So if you do bag of words on it, both of them have same feature vector. Why? because you have removed the structure of the data. Okay, you have just some unstructured frequency count of the words, and you can see why this would be the problem. That's one problem. Okay, what other problems do you guys foresee? Then it can give importance to some words which are unimportant. Typically, if you have enough data, it would not happen, because it would learn to see that, okay, these are the important words. Okay, but some things it would be unable to do, which is these type of cases, because of course they are exactly same feature. So it's same point in the data, represented once as a sentiment of 1, once as a sentiment of y. So whenever you have frequency of like not and good and bad, it would just say neutral, because it would not be able to do either. But the stop words, it would learn automatically that these are unimportant, because stop word would be present in neutral sentences, in positive sentences, and good sentences with equal probability. So we'll see what stop words are. Just go with us for a second. Okay, so from an engineering point of view, okay, not from a learning point of view, from engineering point of view, from assigning resources and creating network, what is the issue with this approach?
Which is we cannot capture the language features such as sarcasm or other techniques that we use in GMT.
100%, yes, you're right. Would not be able to capture it. So anything context-based would not be able to capture it. Okay, so these are context information for this. In these type of methods, it's absent. Okay. What about another problem with this? What is the issue with having vectors like this? Okay, so but having sparse vectors is not necessarily a bad thing. Yes, because these are very big vectors. Okay, so dictionary size would be something like 70,000, 80,000. Dua, can you check what is the vocabulary size on GPT-3? Okay. So vocabulary size can be fairly large. Okay, so these are very large vectors for very small sentence. Okay, so there is lots of redundancy. Okay, and I'll motivate something. Essentially, the whole idea of embeddings is this. It says that, can I do something better than this? Can I take a sentence or a piece of text and represent it in a 1,000-dimensional vector, or a 300-dimensional vector, or a 500-dimensional vector? That's the whole idea of embeddings. Okay, but we'll come to it in due course. Okay. So these are long sequences. Okay, and the information is fairly sparse. Okay, it would have been perfectly fine if these were small matrices, small vectors, and sparse. It's fine, but very large vectors which are sparse, so there is lots of redundancy, lots of zeros which are.
This is not in context. Basically, stuff we don't have the notions we have right now. There was a to the positive words in the vector, negative words in the vector, and use them just those.
Yeah, that would be better
Instead
than
of
this.
the whole
Yeah.
dictionary.
Certainly, that would be better than this. Okay, so the fix for this is embedded. But we will go there. We will see it. So embedding is basically, the idea is this. So you have some text, okay, and you want it to be represented by a fixed size vector. Okay, you guys might have seen RAGs. Okay, these are based on these embeddings. Okay, in transformers, there is typically an embedding layer above tokens, and then these embeddings are fed into the further layers of the transformers. Okay, so essentially extracting essential information from syntax in terms of a vector. Okay, how do we do it? So a little bit, we'll go there. Okay. So we have seen what NLP is. We have seen also what we want in our NLP model. We want our NLP model to understand deep context. Okay. We don't want to understand just a few words here and there. So you see that a person might be saying something very complex to a language model, and the language model might be hearing just a few things. Okay. So we wanted it to be, as you mentioned, we wanted to understand complex things. Whether we still don't have evidence whether language model can understand these very complex things. Just know that given enough context, it can learn a very good distribution on it, and sample from it can do something. So a few terms that I would use in this course. You might see terms like corpora. Corpora is a corpus or corpora. This is basically the collection of text that you are working. Okay. So in NLP in 80s, 90s, and 2000, we had some collected data sets. Yeah. We had data set like Newswire, Brown corpus, etc., etc. Now we are beyond that, because we are doing NLP at very, very large scale. We're literally using the entire internet for certain applications. Okay, but this is traditionally when it's a corpus, it's basically the text that you're working with. In your application, you might have some specified corpus for supervised fine tuning or for reinforcement learning with human feedback or something like that. But corpus is the body of text that you're working with for an application. The next concept is a vocabulary. Vocabulary is a set of words that are represented in your language, in your slightly difficult. It's how you break language into pieces, which your network should be able to understand and output. So, you look at languages in general. If you look at languages, the frequency of words in languages is something called power law. So essentially, what would happen is that the frequency of 10 words, the number of times the first 100 words occur, would be the same as the number of times the next 1,000 words occur. Okay. So it decays with the power. Okay. But it has a strong tail. It keeps on going. It's not like English is just, let's say, 10,000 words, or English is a million words, or English is 10 million, many words. So now the question arises, how do we ensure, so if you look at, let's say, the state-of-the-art language models that we have, they can essentially write English very well. They understand everything in English. The question is, how do we represent it to the language model? We saw that we have these vectors, right? Okay, these vectors would become very large. You look at every word in English language. Do you guys have a solution for that? Okay. I'm sorry. Okay, so even if you stem the words, still the dictionary would be very large. So stemming is basically what our friend is saying is stemming is, so I have a word jump. Okay, I want jump, jumps, jumper, jumping, jump. I don't want separate tokens for them. I want one token for it, and then maybe a token for ing, s, and so on. Okay, because if you take the cross combinations, it would become very large. Okay, that's that. But even with stemming, the dictionary size will be fairly large. Okay, I'm going to take a step back. Okay, I'm going to say that if you guys have to represent English language, you guys have to create a representation for it for a computer to understand with the smallest dictionary possible. What would that be? So essentially, if I give you any sequence of any English sentence, you have to convert it in a sequence of tokens. Okay, where the number of the dictionary, the size of the dictionary would be the unique tokens that you can have. What is the smallest number of unique tokens that you need to have in order for for you to convey the information of the language to a computer? Think smaller. So think smaller. You are still at the level of words. Think smaller. Okay. So we have a way of representing language in terms of character. There are characters. Well, let's say that we don't take any applications. We only need 26 characters to represent the entire language. That's how we teach it to our kids. Right? So we first teach them 26 characters A to Z, and then represent the entire English language in terms of these 26 characters. Can you take a step even below that? Can you go below that and do even lesser number of characters or tokens for a computer? You can go binary. Okay, so you need 2 characters for a language to be represented, minimum of 2 characters for a language to be represented for a computer. But the issue with that is that if you, for example, the sentiment that I was trying to convey here, in my data set, I said that this has 5 words. If I make it character level, then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, something like 20 characters. Okay. And then if I do binary level, okay, let's say I take ASCII representation, I have 4 bytes for each character, then it would become 32 times 20, so 320 and 640. Okay. So you see that if you increase if you decrease the dictionary size, the sentence length increases. If you increase the dictionary size, the sentence length decreases. So somewhere you have to find a nice balance in between. And the nice balance is, so what's the dictionary size on ChatGPT? You have to be a bit loud. 50,000. Okay, so we have decided 50,000 is the unique tokens that we need in GPT. Okay. Now the question we should ask is that okay, the words are quite a lot. How do we break it down into 50,000? The idea is I'm going to explain it later, but I'm going to give you the high level idea. The high level idea is that the frequent words, we use them as words. Less frequent words, we break them into characters. Okay. The simplest example, I'll tell you take 49,974 most frequent words, take them as is. The rest of the words break it down into 26 characters. Make sense? It's a very naive approach of writing entire English language into 50,000 tokens. One second, let me repeat. I'll say take the 49,974 most common words. Okay. Use them as tokens. Rest all the words, break it down into characters. So the entire English language for you would be there's 49,974 words and then 26 characters. So 50,000 is your dictionary. See, it's a neat way. We will do it efficiently. We'll see how to do it efficiently, but that's a slightly later topic. Okay. So essentially, we have to find a trade-off between the dictionary size of your vocabulary, and the sentence size. So you can go at one extreme where the dictionary size is small, okay, but then the sentences will become very long. Or you can go to the other extreme where the dictionary size is small, okay, but then I'm sorry, other extreme is the dictionary size is very large, okay, then the sentences would become very small. Everybody is with me? Sure. Okay. So in the very extreme case, I can write every English sentence as a unique token. So I can represent this entire sentence as one token. But you can see that this is a very problem, and this would grow very quickly. So if you let's say I have 10,000 words in my dictionary, and I want to write all unique 5-word sentences, this would be 10,000 to the power 5. So the dictionary would blow up. Okay, so somewhere you can find this type files. Okay. 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 So we understand vocabulary, we understand how to handle it. Even if the vocabulary is very large, the legal vocabulary is very large, our language dictionary can be reasonable size. We have done some feature extraction. We have seen some sparse representation. Let's try to create a better feature. Okay, for the case of sentiment analysis. Okay. So what I'm going to do is I'm going to look at the entire vocabulary. This is a data set that I have for sentiment analysis. I have some sentences. Okay, I'm happy because I'm learning NLP. I'm happy and I'm sad. I'm not learning NLP and I'm sad. 4 sentences. Okay, 2 of them positive, 2 of them negative. Okay. The first thing what I do is I collect the vocabulary. Okay. Small data set. Okay. I can go for word level tokenization. So each word is I created a vocabulary. Next, what I do is I will just look at the frequency of each word in my vocabulary in the negative and positive causes. Okay. So I start looking at how frequently is a word used in my positive sentences and how frequently is a word used in my negative. I'll simply count it. So for example, I start by looking at happy. Happy is used twice in the positive corpus. So I put 2 here. Happy is used 0 times in the negative corpus. I put a 0. Let's look at
Professor,
yeah.
some of our colleagues said there is an echo in the Zoom.
Okay. Is someone's microphone on? Anyone who is in Zoom, their microphone is on. Can you put on? Okay, how about now? Is the echo still there? Okay. Is the echo still there? Yeah. So while we're waiting for the people, what time is Zohar these days? What time do you guys take your lunch break?
Actually, don't take lunch break.
So I'm sorry, what do you guys do?
So basically, we don't take the lunch break.
We just
we
pray.
leave at 8.
You leave at 2. Okay. Let's do that. We'll leave at 2. We'll not give you any lunch break. We'll just take a prayer break
Yeah.
and we'll come back. So what time is Zohar?
Time for there as well.
12:06. So we'll break from 12 to 12:30. Okay. Okay. So 12 to 12:30 we'll take up. Okay. So the echo is fixed. Okay. So the echo is fixed. Now we'll look at let's look at the count of the word I in positive and negative corpus. Okay. So how many times is I used in the positive corpus? 1, 2, and 3. So in the positive corpus, it's used 3. How many times is it used in the negative corpus? 1, 2, 3. Okay. So you will see that I will put 3 and 3 here. Okay. Let's look at another word. Let's say sad. Okay. So how many times is sad in the positive corpus? 0. How many times is sad in the negative corpus? 2. Okay. So I'll put sad 0, and 2. I do it for all the words in my vocabulary. Okay, everybody is with me? Yeah. So I create a list of my vocabulary, and then I just count how many times the word is used in positive corpus and in negative corpus. Okay, I create this. Now, based on this, I can create a feature. Okay. Can somebody tell me how I can do that?
Unique, the happy and sad. Because it's not present in the positive, but present in the negative and vice versa.
Okay, okay, but you see that now you are just visually inspecting it and making this decision.
Yeah.
But this might be long. It might be too many things. And can we do a more structured way of doing that?
The words that frequently presented in the positive but not negative, and the opposite.
Okay, so I'm going to give you an example. Okay, so happy is present more in positive corpus, right? If I give you a sentence which is all happy, what would you say? If it's a sentence which has 3 happy in it.
It's more likely than not, it's happy.
Exactly, exactly. So what I would suggest is that we create a feature based on the frequency of words in a sentence in the positive corpus and the frequency of the word in the negative corpus. So essentially what our friend said is that we are looking at, if I have a sentence which is happy, 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 I'm saying that it's a positive sentence. Why? Because happy is present more in the positive corpus. Frequency of happy is more in the positive corpus. So essentially, what if I take the frequency of all the words in my sentences in the positive corpus? So essentially, what I will do is, let's say you have words in a sentence, W1, W2, W3, and WN. Okay. So use WN. What I will do is I will create a feature or a component of a feature where I will say that go from I equal to 1 to N and look at the positive frequency of the word WI. Add them up. Okay, so I'll give you an example. Let's say I have a word, I am happy. Let's find what this is. So how many times is I used in positive corpus?
1.
No, 3. How many times is M used in positive corpus?
3.
How many times is happy used in positive corpus? This is it. Okay. This is basically the weight of the words in a sentence in the positive corpus. How many times have I seen these words in the positive corpus? Of course, you can do the same for negative corpus as well. Okay. So I will do this is, let me call this the first component of my feature. The second component of my feature is summation from I equal to 1 to N. Negative frequency, WI. Okay, because all the words I need to do it. Okay, let's do it for I am happy. So how many times is
3 to 6?
Okay. So this is 3 times, and 0 times. So it's 6. So now you have second component of this is 6. In general, it's always nice to have a bias term in your feature. Okay. Why? Because if you don't have a bias term and you're looking at a linear decision boundary, the linear decision boundary would have to go through the origin. It's not necessarily a good thing. Okay. We want the ability for the decision boundary to be anywhere. So we will create a feature which would be a bias term, summation of the words in positive frequencies, plus summation of, summation of the words in the negative frequency. Okay, this is your feature. Now you can create, it's a 3-dimensional feature, and you can create it for any sentence, a sentence of any length, you can create a 3-dimensional feature. Now this is like a smarter feature engineering. Okay, so you create these. Now what would happen is that all the sentences in your data set, okay, they would give you a 3-dimensional feature. You can collect them and it would look like this. So now your data set is a problem where you had a variable length sentence and a fixed set of classes. Now you have converted it. X is in R3 and Y is in. In this case, we have just positive and negative, I think. So it's a binary classification, 0 and 1. Okay. So you see, if you do smart engineering, this, by the way, is what people were doing in the 90s, early 2000s. This was very common. Okay. Very similar approach to this was used, like, for example, for spam detection in emails. Okay. Okay, now that you have this, can you use your normal machine learning algorithms to do some learning on top of it? Okay. Let's look at the simplest classification algorithm that we have. What is that? Simple classification, the simplest classification algorithm. Logistic regression. Okay. So let's say we do logistic regression. Guys, I will do a review of logistic regression and you guys will tell me everything. Okay. So please don't tell me that we don't know what logistic regression is. I will die of sadness. Okay. So let's look at logistic regression review. So you have X, okay, which is 1, okay, for the first data point, the first feature, for the second data point, the second feature, and 1 for the second data point, the first feature, and for the second data point, the second feature, for the nth data point, the first feature, for the nth data point, the second feature. So its shape is number of data point is, let's say, n times 3. This is your data. Y is, of course, just a number. It's from a set 0 and 1. Okay. So how do I set a logistic regression model for it? Okay. So first do the linear transformation. Logistic regression has 2 components, right? There's a linear transformation, then it has a nonlinearity. Okay. It's a 1-layer neural network. Okay. So what is the linear part? So just bear with me 1 second. So let me write the y vector as well. The y vector would be maybe 1, 0, 1, 0, so on. Okay. And it has its n time 1. Okay. Why am I writing this? Why am I'm telling you what is the shape of y hat? Y vector, because we would need y hat vector to be of the same shape. You'd have to do y minus y hat at the very end. Okay. So now let's come back and let's see what would be the linear transformation. You have x, what would you do? Multiplied by w. Okay. So why am I multiplying x with w and not w with x? Because you can see that the output shape I want n, right? Yeah. So I have to keep this, which means I have to do multiplication on the right hand side. Okay. So I'll multiply it with the weight vector on the right hand side. And because of this shape, I know that the weight vector has to have 3 components. Okay. Let me call it theta. Okay. So this is a theta vector. So I have to do x theta. This is the linear transformation. I'll call it z. Okay. What do I do after that? It's a binary classification problem. So which non-linearity can I use? Can use sigmoid. Okay. Then I take this and I do y hat, which is sigmoid of z. Okay. Let me make it a vector. 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 Okay. So now you have y and y hat. Okay. How do I set up the loss? Okay, cross entropy loss. Okay. So I'll have a cross entropy loss, which is summation over I y log of y hat minus 1 minus y log of 1 minus y hat for the ith component. P plus. Okay, and what do I have for this entire loss? There's a minus sign outside. It's a binary cross entropy loss. Okay, everybody's with me? Sure? So hopefully quiet. Okay. Okay, so now what do I have to do? I have the loss between y hat and y. Okay. What do I do after that? Minimize it how? Okay, I need to minimize this with respect to theta, but how do I minimize it with respect to theta? Okay, gradient descent. Okay, so guys, in machine learning, whenever you are minimizing something, you are doing a version of gradient descent. Okay, there is no other way of minimizing things in machine learning, deep learning, other than gradient descent. It would be some modification of gradient descent, but in general, the algorithm would be gradient descent. So first I would need to calculate its gradient. Okay, somebody help me calculate it? Guys, this is very basic thing, so we need to do it. No, I know. So we'll use gradient descent or a variant of gradient descent, which can be stochastic gradient descent, or which can be an Adam optimizer, or which can be any other momentum-based optimization. But for all of those, first you need to calculate the gradient. How do I calculate the gradient of this with respect to theta?
We take one,
Hmm.
then make forward plus,
Hmm.
see the output, then we update the.
Okay, that's fine. Okay, so in code, typically when you're writing a PyTorch code for this, you do the forward pass, okay, and the backward pass is handled by the library for you, okay. But I'm asking mathematically, how do you calculate the gradient? Of course, somebody has to write the code for it for the backward pass. How did they write it?
The new W
Hmm.
is the last W, plus the.
I know. It's the old W minus learning rate times the gradient, okay, of the loss function with respect to W. But what is this gradient? How do we calculate it? Yeah, but how? Like how do I calculate the derivative of this? So what I'm telling is that I need the gradient of the loss function with respect to theta. So I'm asking you, how will I calculate it? Chain rule, okay. So let's do it step by step. So let me just write it like this. Okay, so the first thing is that can I take the gradient inside the sum? You can take gradient inside the sum because derivatives are distributive over sum. Yeah, this would become negative summation I. Okay, now is yi is label of your data function of theta. Label of the data. No, label is not function of the data. Label comes with the data. Okay, so it's constant. Okay? So just y hat is a function of theta because you change theta, z changes, and if z changes, the sigmoid of z will change. Okay, and sigmoid of z is y hat. Okay. So you can use this as a constant and you take the derivative of log of y I hat with respect to theta. Now you apply chain rule. Okay. So I know that y hat is function of z, okay, and z is function of theta and x. Why? Because what was z? Z was x theta, and then y hat was sigmoid of z. So in order to find the derivative of y hat with respect to theta, I'll take the derivative of y hat with respect to z, and then the derivative of z with respect to theta. So let me do it. So the derivative of log, okay. So I'll do one step more. Okay. I'll say that log of y hat is a function of y hat, and then y hat is a function of z, and z is a function of theta. Okay. So first thing, I'll take the derivative of log of y hat with respect to y hat. So what is the derivative of log of x with respect to x? 1 over x. Okay. So this would be 1 over y hat I. Okay. Next, what is the derivative of y hat with respect to z? Remember, z is x theta. Oh, sorry. Z is x theta and y hat is sigmoid of z. So I first need to find the derivative of y hat with respect to z. I need to find the derivative of sigmoid with respect to input of the sigmoid. Okay. So what is a sigmoid? 1 divided by 1 plus exponent minus z. Okay. Just to ensure that, how would I ensure that this is indeed sigmoid? So a sigmoid, when z approaches positive infinity, sigmoid approaches 1. Okay. So let's put z positive infinity, z approaching positive infinity here. Minus z would become a very negative number. Exponent of very negative numbers is 0. 1 divided by 1 give you 1. Okay. On the other side, when z approaches negative infinity, sigmoid has to approach 0. Okay. Yes. So when z approaches negative infinity, minus z would approach positive infinity. Exponent of positive infinity is a very large positive number. 1 divided by a very large positive number approaches 0. So this is indeed a sigmoid. Okay. Can somebody tell me, or can somebody prove that this is a monotonic function? Monotonic function is always increasing or always decreasing? How would I? Yes. No, it's I know it's shape, but we know that this is its shape because somebody drew that shape for us, because we certainly did not find the function at odd point ourselves and plot it. Okay. If I were to give it to you in the exam and say the proof that this is a monotonic function, how would you do it? Second derivative. You don't need to go to second derivative. Okay. So if the first derivative is always positive or always negative, then it's a monotonic function. Okay. If the first derivative is always positive, which means this is an always increasing function. If the first derivative is always negative, it means it's always decreasing function. So when you calculate its derivative, which we'll just do, you will see that it's always positive. Okay. So let's calculate the derivative of this with respect to z. Okay. So this is 1 plus exponent minus z to the power minus 1. Derivative. I'm just going to bring the denominator into numerator and make it a power of minus 1. Okay. Now I will apply chain rule. Okay. So what would be the derivative of x to the power minus 1 with respect to x? Minus 1, x to the power minus 2. Okay. Simple power rule for this. So let me do that. So I'll have minus 1 plus exponent minus z to the power minus 2. Okay. Remember, I'm applying chain rule. So I just first took the derivative of this quantity with respect to this whole thing. Okay, so consider this whole thing as, let's say, a u to the power minus 1 derivative with respect to u is just this thing. Now I have to take the derivative of this thing with respect to z. Okay, so
minus exponent minus t.
okay, so it would be exponent minus z times minus 1. Okay, so the derivative of exponent minus z with respect to minus z is exponent minus z. Derivative of minus z with respect to z is minus 1. Okay, so in general, guys, I don't want you guys to be like very big mathematicians, but simple chain rule is a must. Okay, there is no avoiding it, and it would make your life easy in places where you don't expect. You just need to learn it once, learn it well, and that's it. Believe me, we don't revise chain rule every time we come to the class. We just did it once well, and that's it. It stays with you, and you can build on top of it. Yeah. So we do a little bit of simplification. So this minus 1 will go away with this minus 1. So you'll have exponent minus z divided by 1 plus exponent minus z to the power 2. Okay, now I can do some arithmetic simplification. So I can add a plus 1 and a minus 1 to the numerator. Why I'm doing it? Because I want to get the same term in the numerator as I have in the denominator, because it would allow me to cancel a few terms. Okay. So I can simplify it as 1 plus exponent minus z divided by 1 plus exponent minus z whole square minus 1 divided by 1 plus exponent minus z whole square, and then this cancels out, the other things remain itself. Now, what can you tell me about this quantity and this quantity? It's the same thing. Okay, so essentially this is. And what can you tell me about this quantity and this quantity? It's the square of it and minus. Okay, so it's minus. Okay, and which you can simplify to sigmoid of z. That's the derivative of sigmoid with respect to its input. You can replace it in our expression. Let me do a little bit of simplification. So sigmoid of z is y hat, right? And 1 minus sigmoid of z is 1 minus y hat. So if I replace it with y hat, 1 minus y hat, okay. I do it for the second quantity. So again, 1 minus y would is a constant. It remains as is. The derivative of log of 1 minus y hat with respect to y hat is 1 minus y hat in the denominator times minus 1. Okay, and the derivative of minus y hat with respect to z would be just this quantity times minus 1. This becomes positive. Okay, so now you have some terms, you do a little bit of algebra on it. Okay, and if I'm not wrong, this would turn out to be, let's actually do it. So summation I, yi divided by this things and this thing goes away. Okay, things and this thing goes away. Okay, yi times 1 minus yi hat plus 1 minus y times y hat. Okay, and if I do a little bit of simplification for it, this would become yi minus yi hat minus yi hat minus yi hat. Okay, I think there's a minus sign here somewhere because these things go away. Okay, and it becomes yi minus yi hat. Let me see where I've made a mistake. I will fix it in a break. Okay, but essentially you will get summation I, yi minus yi hat, and that's it. That's your gradient. Okay, so you implement this gradient and then take steps in the negative gradient descent, negative gradient direction. And just for completeness, by the way, once you have the gradient of the loss function with respect to theta, okay, what would you do? What would be theta at time t plus 1? What is this step in the negative gradient direction? Theta at time t minus learning rate times gradient of the loss function with respect to theta for values of theta at time t. Okay, that's it. You do it multiple times and you will get a set of theta values which will be optimum once you reach a minimum. Once you have the theta value, how will you classify a new sentence? So let's say I get a new sentence. I was happy to watch the movie. So what will I do? Once this new sentence come in, I have my model, trained model. What will I do? Okay. So I will get the counts and get the sum of positive frequency, sum of negative frequency. Let's say I got it 1, 12, and 9. Multiplied by the weight. Okay. So weight was, let's say, 0.3 and 1 and minus 1. Let me make it 1. 1, 1, and minus 1. So let's do it. This will become 1 plus 12 minus 9, which is 4. Then you take the sigmoid of it. If it's greater than 0.5, you say it's a positive sentence. If it's less than 0.5, you say it's a negative sentence. Okay. So now we did the full pipeline of taking any corpus of text, okay, converting it into a fixed length feature, okay, and doing a logistic regression algorithm on top of it, learning the weights and the ability to classify any new sentence. Okay, everybody's with me? Okay, let's take a short 5-minute break here and we'll resume. What happened to your math? Answer all the math questions. Right? Assalamu alaikum. How are you? See you. Right?
From the beginning of this year, all the courses, there's no exam. All of them, because it's all of them is a practical course, and they evaluate us with the project.
20% or something. 20%. No, we'll not take exam in Ramadan. It would be somewhere in the end of it. I'm not going to bother you. No exam in Ramadan.
If it's.
Yes, can you just
Just.
Let me
we
think
we
about
had
Yeah.
computer vision and also
The deep learning.
deep learning.
Dr. Mohammed and Joshua, all of them, even the computer vision, there is no homework, and only project. They give us a lab after the noon. We work together in the lab. Okay, as a practical, in the final, they give us.
Let me see. Let me see. No, believe me, it's not something.
No, it's the
Because,
exam is
no, no,
very, very basic.
you know why I want to take it, because I want to collect some information about the level of lab. It's not to like, to say like.
You can collect this from.
Yes,
No, no, project
Group
is,
work.
no, project and exam test different about that. So a exam is to test like, something like RAM, like the immediate memory that you have. Projects is, I know projects are more important, and that's why we put much more weight on project than, but I want to understand a few things about this. And it's not, I don't want to test weeks, I want to test myself. So don't worry about it, it's 20%. So even if, let's say you do nothing on the exam, you'll be fine. But don't worry about it, it's just, it's good to have it.
Because you know it's the end of the program.
Believe me, once you see the exam, you will be happy, and you said you want to do it. Believe me. After you take the exam, you will come to me and you say, let's have another exam. Okay, believe me, you like it. It's not to punish you guys. Don't worry.
No, we don't consider it as a
Yeah,
function.
it's a good thing. You will like it.
But since we from the start of this year, all the courses were only projects, so we want to keep the pace same now.
Project is the most important part of this. Project and most is the most important. 20% is nothing. Okay, okay.
Okay, make
Think
it.
about it.
I'll think about it.
Yes, yes,
I'll think
think
about
about
it, and you guys think about it as well. Maybe we do 2 exams. Okay, think about it. If you guys agree, talk to the guys and we'll do 2.
Okay,
Okay.
thank you.
Assalamu alaikum. How are you?
Someone told me that we should be presented the exam at 10.
Forget about it. Okay, I'll handle it. Let's see if you want to do any. You want to give them the sentiment analysis example after the break?
That is, we see.
SVM, yeah, but you can do linear logistic regression as well. It's perfectly fine. You can. Let me.
Actually, this code, yeah, the code has problems, by the way, with the versions.
Yeah, I fixed it. Like it's one thing, so I just use I modified it and did some of my own things. But you can, for example, use logistic regression. I change it to logistic regression. Give it a number of maximum iteration. It's faster. It's better.
Okay, can you use your laptop since mine doesn't work?
Of course. Okay. So you can do it from here. We can like copy and paste or just explain. Go through
Oh,
the code.
explain it
And
to
yeah.
them.
So the feature that I'm using is what?
What's
I'm
that?
using DF IDF, but that's fine. You can just briefly say that this is a feature very similar to what we do. In fact, it's very similar to what
It's
we do.
frequency.
Yeah.
Yeah.
Okay. But good luck.
Thank you.
Yeah. So,
Yeah. We use feature extraction in machine learning, but we didn't use it now in deep learning. Right?
so we will not when we come to transformers, we will not use feature extraction. Okay. This is just to walk you through the journey of like how. So we started in 1950s and 60s. Like
Deep learning handle that.
it will handle it for us. Yeah. Okay. Yeah. Thank you very much. No. Exam is a must. Exam is a must. It's for me. I need to see how good of a job we did.
The project is more applicable.
I know. That's why it's much more weight. It's 40%. Exam is just for me to see like what type of things we have learned.
How to take exam. The
No,
last-
but this is life. Like I said, these are things which you do once in life and you don't forget.
I
It's
think
like
now-
walking and no, we'll be. The thing is just 20%. So don't worry about it. It would be maybe MCQs, maybe just a small set of codes.
Because days when we will take the exam
No, the exam is somewhere in April. I'm not going to take it in Ramadan.
with the another course?
Yeah. At the end of the semester, somewhere I'll find a day and we'll do it.
Just worry, we won't forget.
No, don't worry. Don't worry. We'll be fine. Okay.
Okay.
Just drop one, homework or project or exam.
I draw homework and then make exam.
No.
Why do you think about project and homework?
No, because I think it is access to learn a little bit about what type of job we need to pass. What type of knowledge we need. Project is intent that we want to define. That's why we have to see all the courses of project. This one also has component is 80% to join. But a little bit of information about
The issue with us, I think, because
and the classes are all this. Not have any outside. Yeah, of course. That's the main.
زي ما قلت لك أفضل يعني الأخبار عندكم يكلموا بزياد وأنت تتكلم بزياد هو اللي يقدر الشباب قالوا لي كان في موضوع الوعي واللي تحته ما هم موجودين معايا.
Not the sort of recommendation.
Yes. Is it
think,
submitted, right? Or no?
No, you didn't submit.
I will submit it.
Yes,
Yeah.
because I think deadline is maybe 2 days into the.
I will do it. I have to do it for you and
Mm.
for one of our friends. Mhm.
I did my best to write draft,
Mm.
but I think you need to.
No, we will,
revise it.
we'll clean it up. Okay. Yeah. So for the homeworks, it would come with the homework. So when we give a homework, typically it will be 15 days. So end of the course is on second, so it will be like around.
I want to know which is the most suitable day for me.
Mm.
I know the quiz and submission.
I will add it to the website. Okay. I'll add it to the Blackboard.
you.
Okay, thank you. Guys, let's settle down. Okay, Doa, you want to? Okay, guys, so we just saw an example of sentiment analysis. So Doa is going to walk us through how to practically implement it with Python, with sklearn, for IMDb. So very similar to the example that we were seeing. We're going to use a slightly different feature extractor or PDF, some frequency, reverse Shotman frequency, but you can think of it as a proxy for the feature that you saw. It's very similar in broad context, but slightly different experience. Okay, so over to you. Good luck.
Do they have the lab or not?
You have one, I'm sorry?
Do they have the lab?
They don't have the lab. Guys, we will share the lab with you. Okay, once at the end of the day, I will upload the labs to the Blackboard so that you can have access to it as well as the slides. You have to turn it on.
Where?
Turn it on.
صوت واضح؟ فهمت مع دكتور نايم طريقة إنه كيف نسوي فيكتورايزيشن للداتا سيت حقتنا اللي عندنا في ال NLP صح؟ فالحين نعرف كيف نسوي لها بالبراكتيكال يعني باللابات. أول شيء راح أسوي import اللابات اللي أنا أحتاجها. الفيكتورايزر يستخدم هنا اسمه TF-IDF فيكتورايزر. TF-IDF فيكتورايزر فقط يسوي سكورينج للتكست اللي عندي على حسب الفريكونسي اللي عندي يعطيها سكور. هذا هو اللي يسويه يعني. بعدين راح أنادي اللينير لوجيستيك ريجريشن. في موديل ثاني نستخدم اسمه SVC، ناسي عليه اختصار ليش. هو جزء منه، في اختلاف بسيط عن سبورت. بعدين accuracy score عشان أقدر أوجد الأكيورسي حقت الموديل حقي. والداتا ست راح أستخدمها اسمها IMDB اللي هي حقت الأفلام. ترتيب هذه الداتا حقتي عبارة عن two labels negative أو positive مع الريفيو. يعني مثلا هي زي tables يعطيك negative بعدين ريفيو مثلا I hate positive عفوا مثلا I love this movie negative I hate this movie مثلا. وهذا تقدم بس عشان تعطيك أبوريكم هو دقيقة بس progress bar. طيب أول شيء بسويه train data و test data. ال IMDB data set فيها two splits، فيها train وفيها test. فأنا كوني نديت الترين أول test فلازم تكون مرتبة حتى هنا train وهنا test. بعدين لأن أنا راح تعطيني هي iterator. الiterator مشكلته أنا ما أقدر أسوي له access directly، وهذا الشيء ممكن أحتاجه في المشين ليرنينج، عشان كذا أنا أحولها list. طيب تقدم هي بس تسوي هذا البار عشان تشوف إنه البروجرس حقك. فأنا لازم أحول الترين داتا والتست داتا لليست عشان أقدر أسوي لها access directly من لما أستخدمها بعدين في التريننج. أوكي. زي ما قلت لكم الداتا سيت حقتنا عبارة عن two tables. أول table في الليبل negative positive، بعدين الريفيو حقتنا. طيب، فأنا عشان أقدر أسوي لها سبليتنج لواي ترين إكس ترين واي تيست إكس تيست، أقدر أستخدم زب إيش تسوي؟ شوف أنا كم كولم عندي. هنا عندي تقريبا 2 columns، اللي هو واحد حق الليبل وواحد حق الريفيو. طيب، راح تحط الكولم الأول في أول ليبل عندي اللي هو حق الليبل، راح تحطه في الواي ترين، والريفيو راح تحطها في الإكس ترين. نفس الشيء في التست. لو مثلا كانت الداتا سيت حقتي مقلوبة، الريفيو أول بعدين الليبل، راح أعكس هنا أحط إكس ترين أول بعدين واي ترين، والتست نفس الشيء. واضح؟ لازم أسوي فيكتورايزيشن أو الفريكونسي حقت الداتا سيت اللي عندي. استخدمنا TF-IDF فيكتورايزر، أعطيته ماكس فيتشر 5000. زي ما قل لكم إنه أنت تسوون فيتشر انجينيرنج وتاخذون بس الكلمات المهمة مثلا، صح؟ فلو أنا ما خليته ياخذ ماكس فيتشرز، خليته فاضي، راح ياخذ كل الكلمات اللي عندي سواء مهمة ولا مو مهمة. راح يكون عندي الفوكابلر مرة كبير، فما راح ما منه فايدة. عشان كذا حطيتها 5000 عشان بس آخذ 5000 كلمة مهمة اللي عندي حسب TF-IDF سكورز. أعلى سكورز راح آخذها. ما أعرف. أيوة، في مرة قد بحثت كأنه قال 100,000 بس ماني متأكدة. ف100,000 كلمة أحيانا تكون ذا وإز وآن، هذا عشان ما نحتاجها الحين. طيب الإكس ترين فيكتورايزر، يعني ناديت TF-IDF وأعطيت الإكس ترين فيت ترانسفورم. دائما مع الترين نستخدم فيت ترانسفورم لأن أنا أبغاها تتعلم وفي نفس الوقت فيت تتعلم. راح تتعلم إيش الكلمات هذه اللي عندي، والترانسفورم راح تسوي اكستراكشن لهذه الكلمات تحطها في الفوكابلر حقي. طيب، الاكس تيست فيكتورايزر دي ترانسفورم بس لأن أنا ما أبغاها تتعلم مثلا اللي في التست، أبغى نفس اللي في الترين اللي تعلمته تاخذه، الكلمات الموجودة في الترين، مو تروح تتعلم مرة ثانية حق التست كأنها غشت. واضحة هذه النقطة؟
الماكس فيتشر 5000 يعني لو كان في اكثر من كذا ولا
ما راح تكون موجودة عندي في الماتريكس، هو راح يعطيك سبارس ماتريكس، راح تكون بس 5000 الكلمة المهمة، أكثر 5000 كلمة مهمة عندك، الباقي راح يكون أغلبه أصفار. ما راح آخذ. طيب بعدين هنا أنا دربت الموديل حقي الجستك ريجريشن، أعطيت عدد الأيتريشنز حقتي 1000. وبعدين ناديته هنا دوت فيت يعني يسوي تريننج للإكس ترين حقتي والواي ترين من السكيلر. بس هذا التريننج أنا قاعدة أسويه هنا. بعد كذا الواي بريدكشن حقي راح أعطيه الإكس تيست حقتي عشان أعرف هل البريدكشن حقه فعلا كان صحيح ولا لا. عشان أوجد الأكيورسي لازم أعطيها الواي تيست والواي بريد عشان تقارن هل التيست اللي هي الأكشوال فاليوز حقتي هي الواي تيست اللي هي الأكشوال فاليوز، والواي بريد اللي هي الموديل اللي طلعها لي، راح أقارن بينها وبعدين راح أوجد الأكيورسي حقته. هنا الأكيورسي 88 تقريبا. وبس عشان أسوي تيستينج للموديل حقي أعطيته هنا unseen data، أنا كتبتها بنفسي. I was bored during this movie was fun. بعدين لأن يعني الحاسب ما يفهم الكلمات عشان كذا لازم أنا أسوي لها كمان vectorization بنفس اللي استخدمته فوق اللي هو TF-IDF vectorizer. راح أعطي السنتس حقتي وبعدين لازم أسوي له prediction. واحد عندنا يعني نيجاتيف واثنين يعني بوزيتيف. هنا I was bored during this movie نيجاتيف، فعلا أوجدها نيجاتيف. والثانية the movie was fun positive، ففعلا أوجدها بوزيتيف. هل واضح اللف؟ في عندك أسئلة؟
واضح بس الSPC مصر ولا ليش استخدام؟
لو ودك تستخدمها دقيقة. هو عشان هو شرح لكم عن logistic regression فقال لي أشرح logistic regression. السي في سي الاس في سي عفوا ياخذ وقت فاصبر عليه شوية. Yeah, they want to see the result.
They want to see it.
ليش؟ لا هو فعلا يطول دائما هذا الموديل. جي بي يو أصل very nice. شكله أصل. أوكي. عموما I think إنه هنا logistic regression كانت الأكيرسي حقته أعلى. أوكي. You can continue. Yeah. I think خلاص. They said they want to try it later.
It's fine.
The whole lab is basically trying to list the version of SVC, right? I'm familiar with that SVC. I think we can move on.
I finished everything.
Thank you. Thank you, though. Okay. Okay, guys, so any questions? Okay, we'll share the notebook. So in general, the torch text library is, I don't know what's the issue with it. It's generally a bit difficult to get it running with the most recent torch version. So we adjust the torch version such that we can use torch text. And torch text is to get the IMDb data and then run things on top of it. Okay, so any questions? By the way, have you guys seen support vector machines so far in this course? Okay. Yeah.
If we change the theater gate to another vectorizer, then we will have different parts to this problem. So I think would be different. The main question is if I did the best here, or
No. So it's difficult to say which is the best here. It's basically a feature extractor. A feature extractor, we are doing it a priori. We're not learning them. So it's difficult to say which one is best. Okay. Ideally speaking, in modern machine learning, what we do is we learn these feature extractors. So we learn the embeddings. Then we have a claim of saying that, okay, these are the best because these are learned from the data, and well, not best because you're still learning a local minima, but at least you are optimally tuning them for a particular data set. Okay. Okay, so let's continue with the class. Okay, so next what we are going to do is we have created the frequency counts of the terms in the vocabulary and positive and negative corpus of our data. Okay, so we can use that to create a naive-based classifier. Okay, so what I'm going to do is I'm going to motivate a little bit what is Bayes' theorem, and then try to explain how do we use naive-based classifier in our applications. Okay, so in general, in estimation theory, we have certain terms that I want to So typically what you would have, this by the way, is true for all machine learning, is that you would have some data, a data set, which would come from some distribution on your data. So think of it as like probability of X, think of it as a language model. Okay, so it's a probability which tells you how likely a sentence is in language or a set of word is in a language. Okay, all large language models are basically trying to learn this. A large language model can learn this, then it can speak language. Okay, that's essentially what large language models are trying to do. Okay, but the issue is this thing is not typically very easy to learn. It's a distribution of very high dimensional space, and we don't have access to it. Okay, but what we have is access to samples. We have some data. Okay, so what is data? That you have some sentences, right? So let's call it it's one, some sentence, it's two, all the way to some end sentences. You have this. Okay, in this case, this is an unlabeled data, but of course the same is true for labeled data as well. In labeled data case, you will have X, probability of X and Y, as in sentiment analysis, a data and its corresponding sentiment, and you will have this data. Okay, so the question that we're trying to answer in machine learning is, given this data, can I learn probability distribution which is close to this distribution? Because if I manage to do it, then I can sample from that distribution which is close to my original distribution, and I can produce language. This is what large language models are trying to do, and this is called language modeling. Okay. We would look at it in a little bit of detail, but that's essentially the idea. So how do we do it? How do we set the problem up? We say that, okay, we don't have access to probability of X. This is not accessible to us. Okay, but what we say is we have access to a probability distribution P theta of X, which we controlled with some parameters theta. Okay. So think of it as some sort of neural network, which will take in some sentence and will give you a probability value for this. Let's say the probability value for this is 0.1 or 0.01 or whatever. Okay, this is you can create. In fact, we just created one where we took in probability of certain, we have theta, we take in some X, we generate a feature for it, and then we can say what is the probability of Y given X, a certain sentiment for this, this data. Okay. So now you have two things. You have data, which is provided to you, and you have parameters of your network theta. Okay. Okay. So all machine learning, essentially what we try to do is we want to maximize the probability of observing D. This is what we are trying to do in all machine learning. Okay. This quantity, probability of observing D given some theta, I can write it like this, probability of D given theta, certain value of theta. This is called likelihood. So given some parameters theta of your network of your model, how likely it is to observe your data. Okay, it's called likelihood. Okay, and all machine learning is maximum likelihood. You are adjusting theta such that your data becomes most likely. So think of it like this. You are looking for a distribution which can model the language. You don't have access to this probability distribution, but you have access to some samples. Okay, so you have seen some real life sample. Now what you will do is you will try to create a distribution which makes the sample that you have seen more likely. That's the only thing you can do. Okay. Okay. So as I mentioned, probability of D given some theta, this is likelihood. Okay. Then we have probability of theta. These are called priors. Let's say if I tell you that there is some distribution of thetas which are more natural or which gives rise to more natural looking distributions. Okay. That would be a prior. Okay. Typically in machine learning, deep modern machine learning and deep neural networks, we don't have any priors. Yeah. So likelihood is the best thing that we can do. Then we have a third thing, which is posterior. Okay. So posterior is basically given the data, what is the distribution of thetas? Okay. What type of thetas would be more likely if we are given a distribution on our data? Okay. This again is not very widely used in deep learning for obvious reason, because it's difficult to handle. We don't have a distribution of prior. Okay. So now comes the application of Bayes rule. Okay, so what is Bayes rule? Bayes rule can be written in multiple ways. One standard way is that probability of B given A is probability of A and B divided by probability of A. Okay. Or you can say probability of A and B is probability of B given A times probability of A, which is equal to probability of A given B times probability of B. Okay. That's basically different ways of writing Bayes rule or Bayes theorem. Okay. Now let's see how do we use it in our particular application. So remember, what did we do? We took our words and we created a table for it, which shows their frequencies. Okay. So now if I give you this, will you guys be able to tell me what is the probability of observing happy, given that it's a positive sentence?
No, 2. The number of 2/13.
Okay, so it would be, you come to the positive sentence because I'm telling you it's a positive sentence. So you come to the positive one, and then you see how many times is happy observed in positive? 2 divided by 30. So the probability of happy given positive is 2 divided by 30. Can you tell me what is probability of, let's say, I given positive?
3/13.
This is 3/13, and so on. We can do it for all of the words. Okay. If we can do it all of the words, then if you will allow me, I'll do a couple of things. First thing is I will write the probability of a sentence. Okay, let's say you have a sentence X, okay, where the sentence X is basically X1 all the way till XT. These are T words. Okay. So can you write this probability in a way using Bayes rule, which is slightly easier for me to handle? So I have a probability distribution which is on this T-dimensional space where T can be any number. Okay. Can I write this probability? So essentially I have probability of X1 XT. Can I write it in a way which is slightly more convenient for me to handle? Using a Bayes theorem. So I'll take a step back. Okay. Let's say I ask you guys to write an essay on the importance of natural language processing. Okay. So now you got this information from me. You wrote, and you're going to write an essay which explains the importance of natural language processing. Now I'm hoping that you guys would agree with me that you have this information, that you are going to write an essay. Now, when you start writing it, you don't write the entire page. Start by writing a word. Okay. So you would say something like NLP. Okay. Then you have the context of, okay, what you're trying to do, what you have done so far. Then you say NLP is an emerging area. So what have I done? The task of writing this full essay, I broke down into a sequence of words. Think of it if you can do it with this probability. Yes. So what you will do is first you will write a distribution on the first word. Okay. Then you multiply it with the distribution on the second word given the first word. Okay. Then you multiply it with a probability on the third word given the first two words. And all the way till probability of xt given x1 to xt minus 1. Okay. This, by the way, is one of the key intuition that is used in the most state-of-the-art natural language processing. Okay, ChatGPT, Claude, Gemini, DeepSeek, all these models are predicting one word at a time. Okay, it's rather surprising that with the ability to predict just one word at a time, we are able to do such amazing things. Okay? But that's essentially what all language models are trying to do. Okay, everybody's with me? Okay. So now what I'm going to do is, I'm going to try to use this knowledge in naive Bayes. So make a note of it, put a sticky on top of it, we'll come back to it. Okay, we'll work extensively with it over the duration of this course. For today's purpose, I'm going to use a very specific application of this for naive Bayes classifier. Okay. So coming back to, we are going to erase the good essay that we were going to write, and we're going to come back to our original problem. The original problem is sentiment analysis. Okay. Now what I'm going to say is that I have, because I'm not doing any deep learning, any machine learning, I would say what I'm trying to learn is the sentiment. So my theta, the thing that I'm trying to learn is sentiment. The parameter is sentiment. I want to learn, given a sentence, whether the sentiment is positive or negative. So what I'm interested in learning is probability of theta given some sentence. How likely is that this sentiment is positive or negative? Okay. So if you allow me to write it, this would be equal to probability of x and theta divided by probability of x. Okay. Now the thing is, the probability of x is difficult because for probability of x to be available, you need to have a distribution on language. Okay. You need to have how likely a sentence is, which we don't know. You'd have to have a language model. But since theta, I know that theta is two classes, probability of positive and probability of negative. Can I write this as probability of positive given x is probability of x and theta equal to positive divided by probability of x. Similarly, probability of negative given x is probability of x theta equal to negative. These are it's a classification problem. I have these two classes, so I can write it like this. Now let's say for a sentence, if I tell you that probability of positive is greater than probability of negative, what would you predict? You would predict that this is a positive sentence. Okay. If for a sentence probability of positive is less than probability of negative, given a sentence, you would say that this is negative sentence. So essentially I have to just compare these two quantities. Okay. And I'm hoping that the bigger and smaller, the order of these sentences would not be changed if I multiply it with a positive number. Okay. Are you guys following me? Okay. So if I multiply this with a positive number, and I multiply this with the same positive number, whichever one of them is greater would not change. Okay. So since, what is this probability of x? It's a positive number. It's a probability. It's same in both of these. So which means is that I can Get rid of it. Okay, so I will reformulate the problem slightly. What I will do is I'll say that I will divide probability of positive by probability of negative. Okay, if the answer is greater than 1, I will say it's a positive sentence. If the answer is less than 1, I would say it's a negative sentence. Okay, everybody's with me? So how you're seeing that I'm using these small tricks here and there to make my life easier for this particular problem. Okay. So what I do is I say that I will do probability of positive given a sentence X, probability of negative given a sentence X is probability of X and theta equal to positive divided by probability of X whole divided by probability of X, theta is negative. Now these two cancel out. So the bad thing, the difficult probability that I had needed to take care of, it's gone. Okay. My problem is simpler now. And all I have to do is I have to do probability of X, theta equal to positive divided by probability of X, theta equal to. Okay. Everybody's with me? Okay. So now in general, what would happen is that you would not have any distribution of theta. So you would not know whether positive data is more likely or negative data is more likely. If you know, you will use it. But in general, you would not use it. So what is a fair thing to do is to assume that it's equally likely for positive and negative to be there. Okay, independent. So we say that it's equally likely to observe positive tweets, it's equally likely to observe negative tweets. So what we do is, what essentially I'm saying is that if no information is given, you can assume probability of theta equal to positive equal to half and probability of theta equal to negative is half. Okay, so it's a balanced data set because we don't know any prior information on it. So if you do that, then if you will allow me, I will use Bayes' theorem again. And I will write probability of X given theta equal to positive times probability of positive divided by probability of X given theta equal to negative time probability of theta equal to negative. And since both of these are half, this will cancel out. So I will just simply look, given the positive, given that the tweet is positive, how likely is this sentence? Given the tweet is negative, or sorry, the sentiment is negative, how likely is this sentence? I'll take the ratio. If the ratio is greater than 1, let's say it's positive. If the ratio is less than 1, I'll say it's negative. Okay, everybody's with me? So now we are going somewhere. We are going in the domain which we can handle. Likelihoods is something that we can handle. Okay, now one last thing. What is this naive in naive Bayes? So I know we are doing Bayes because I'm writing probability of X as probability of X1 times probability of X2 given X1 times probability of X3 given X2 and X1 all the way till probability of XT given X1 to XT. Now, this, by the way, is not an approximation. This is an exact quality. Okay. Can we show that this is indeed an exact equality? So let's do this. Let's use the Bayes theorem on this. This would be what? So what is the product of these two? Probability of X1 times probability of X2 given X1. Probability of X1 and X2. What is the product of these? It's probability of X1, X2, X3. What is the product of these? X1, X2, X3, X4. So iteratively, you're seeing that you will get probability of X1, X2, X3, X4 all the way till Xt. Okay, so this is an exact equality. Okay, now what make X2? Okay, so we are looking for each word. So this is 3 over 13, or sorry, 2 over 13 for happy, times I have two words which are not there. Okay, which is an issue because generally if a word is not there, you'll have to put the probability equal to 0 there. Okay, which would make the entire probability 0. Okay, and this is one of the problems that we need to solve with language models. But for now, let me assume something. Let me say that I won't consider these. I would just consider the sentence to be happy and learning. Okay, so what is the probability of learning? For positive, it's 1 divided by 13. This is the probability of the sentence given that it's a positive sentence. Now I will calculate the probability of the sentence given that it's a negative sentence. What would that be? It would be happy is 1 over 12. Okay. This might be, the sum might be 13, but I'm not going to leave it as is. And then learning is 1 over 12. Okay. So we do 1 over 12 times 1 over 12. So we'll do the ratio. If the ratio is greater than 1, we'll say it's a positive 3. If the ratio is less than 1, we'll say it's a negative 2. That's naive way. This was used in about early 2000 in email and spam filters and things like that. Okay. Okay. So now a question. So we had these words, right? 2 and B. And we said that probability of, because 2 is not present in positive, B is not present in positive. So probability of 2 given positive is 0. Probability of B given positive is 0. These are words which are not in our corpus. How do we solve for this problem? Any suggestions? I'm sorry? Increase data. Yes, we can increase the data, but there might be cases where, for example, there might be words which are not present in negative tweets at all. Okay. For example, there might be some word for happy, which people don't use with not, and it's only positive in positive corpus. It's not present in negative corpus. What do you do in that case?
Leave all small like 2 and clean data before. Just
okay, you can do it. You can do, for example, remove the stop words and the words which are not important. But if there is a word which is important, let's say there is a word which is present in positive tweets with very high frequency, but it's absolutely not present in negative corpus. It can happen, right? So, for example, let's say that Arabic language was such that we did not use phrases like mabsut. Okay, mabsut was just used as a universally positive thing without modifiers to it. Then you would see that mabsut would be present in positive tweets. It would not be present in negative tweets. Okay, so any tweet which had let's say a mabsut in it, it would always get 0 probability for negative. So we want to have a mechanism where we can remove these absent things, do something for this absent thing. And this technique was quite popular in the classical NLP tools, and it's called Laplacian smoothing. Laplacian smoothing. Okay. And what Laplacian smoothing did was that it said that when you're calculating the probability of a word, okay, probability of word given positive, okay, this would be the frequency of the word, okay, in positive corpus, of course, plus 1, okay, divided by the total frequency plus the vocabulary size. Okay, so now words which are not present in positive will get a probability of 1 by V. Okay, 1 by this, by the way, means size of the dictionary. When you write this small, it means size of the dictionary. Okay. So now you will not have these issues of zero probabilities. Okay, all the numbers, all the words in your dictionary would have some probability. Okay, and the smallest probability would be 1 over the size of your dictionary. So now you will, your problem is essentially solved. Okay, everybody's with me? So if a word is not present, for example, if 2 and B are not present in positive, I will automatically give them a probability of 1 divided by V and 1 divided by V. Okay, so this is another thing that we need to be aware of. Okay. Last point that I want to convey to you guys is that in naive ways, there might be cases where prior is provided to you. Okay. Yeah.
How this simple word is treated as similar to constant.
So why is it helpful? Okay, it's helpful. Remember that we are saying that probability of a sentence, given a sentiment, given some theta, this is equal to the product from I equal to 1 to t, probability of xi given theta, right? So you are just taking the probability of the first word given the theta, multiplying with probability of the second word given theta, probability of third word given theta, probability of fourth word, multiplying all of these words. Let's say that let's say your sentences was happy to be of service. Jack. This was your sentence. Now, you can imagine that these words, if you have enough data, if you have large enough data, these words would be present in the positive and negative sentence because these are common words in English. But this one might not be present. It's a name, Jack, right? So this is, if I ask you whether this is a positive sentence or negative sentence, what would you say? It's a positive sentence. It's not conveying a negative sentiment. It's a positive sentiment. But if you look at probability of Jack in your positive corpus, it would be 0. So the high probabilities of all the other numbers would be multiplied with the probability of a word, which is 0, and the entire thing would become 0. It would collapse. So in order to prevent that, what we say is if something does not exist in a corpus, it has a very small probability. Okay, make sense? That's the advantage. Okay, so coming back to our point, the setup that we developed so far, this was for the cases where we don't have any prior. We don't know whether positive text is more likely or negative text is more likely. So we just look at the likelihoods. So under the assumption that the tweet is or the text is positive, how likely is this text? Under assumption that the sentiment is negative, how likely is this text? And whichever one has a higher probability, we say this is the sentiment for this data. But if I give you a prior, if I say, let me give you an example. Let me say that probability of a sentence given positive tweet is 0.6. Let me say probability of X given negative is 0.4. Okay. If I don't give you any prior, okay. If you don't give any prior, it's valid assumption to assume the positive and negative text is equally likely. What would you say is the label? Positive. But now if I tell you that probability of positive tweets is 0.1 and probability of negative tweets is 0.9. What would you do now?
Find this probability to be weighted.
But how? Like, remember, what are we trying to do? We are trying to find out probability of theta given text, right?
First, we simplify it by, we say it's 0.5 over 0.5 when we take it out, but now we need to consider that in our formula.
Okay, yes, that's exactly what we would do. So we would say that probability of theta equal to positive given x and probability of theta equal to negative given x. Let's calculate that. Okay, so what is this? This would be probability of x and theta equal to positive divided by probability of x, not positive. Okay, and the second one, the bottom one, would be probability of x and theta equal to negative divided by probability of x. We don't know probability of x. Probability of x is same in both, so we can remove it and we can say this is proportional to, this is proportional to. Remove this. So now we have probability of x given theta equal to positive. We will multiply it with probability of theta equal to positive. Similarly, we have probability of x given theta equal to negative. We would multiply it with probability of theta equal to negative. And we will look at the ratio now. So previously the ratio was 0.6 divided by 0.4. Now it's 0.6 multiplied by 0.1, 0.4 multiplied by 0.9. And you would look at it. If it's greater than 1, it's positive. If it's less than 1, you would say it's negative. Okay. So let's do a quick example of this. Give me 1 second. Yes. Okay. So remember what am I trying to do? What is the ultimate goal of this entire setup? I'm interested in finding probability of theta given x. I'm interested in this. Okay. In general, as I mentioned, this is probability of x and theta divided by probability of x. Okay, which we don't have. Probability of x we don't have. It's very difficult to find, so we will never go into cases where we have to calculate probability of x. Okay, now come the next step. The next step, if you want to find probability of x and theta, this you can write it as probability of x given theta times probability of theta. In general, in most cases, you would not be given, this is called a prior. You would not be given a prior. You would not be told whether positive is more likely or negative is more likely. So you would have to assume an equal prior, and you just have to look at the likelihood ratio. Okay. But if you are given a prior, then you should use it. So I'll give you an example. Okay. Let's say when we do these tests for, let's say, certain diseases which are very unlikely to be present, we should use that prior in the calculation. Okay, because it would be more likely to get a false positive than it would be to get a what is it? A true negative. Okay, sorry, a false negative. I'm sorry. So that's basically the summary of this. So in general, if no prior is given, we'll just work with likelihoods. If the prior is given, then we can look at the ratio of the posteriors. We cannot calculate the posterior because we don't have the probability of x, but we can calculate the ratio of the posterior because probability of x would cancel out from both sides. Okay, so let's try to solve this question and let's try to see if we follow it. So let me read it. So we want to find conditional probability using Bayes rule. So we have, suppose that in your data set, 25% of the positive tweets contain the word happy. Okay. You also know that the total of 13% of the tweet in your data set contain the word happy. Okay. And that 40% of the total number of tweets are positive. You observe the tweet happy to learn NLP. What is the probability that this tweet is positive? So you are finding probability of positive given X. Okay. So let's try to do that and let's try to see if you guys can solve it. When someone finds the answer, please let me know. Okay, when someone finds an answer, please raise your hand and let's have a look at it. Okay, you guys, so we have solution from one of your colleagues. Do you guys want another minute for it? Okay, so what is the question answer? Let's start from the start. So it says, you observe the tweet, happy to learn. What is the probability that the tweet is positive? Okay, and what do we have in this question? My phone is on. So what are we given? We are said that 25% of the positive tweet contain the word happy. So probability of happy given positive is 0.25. Okay. Next, we are told that probability of, you know that the total of 13% of the tweet contain the word happy. So probability of happy is 0.13. Okay. Of all the tweets, 13% contain the word happy. And the last is okay, contain the word happy, and that 40% of the total number of tweets are positive. Probability of positive is 0.4. And now you are asked, you're given this sentence, it has the word happy. So we need to find what is the probability of this tweet being positive. So we are interested in finding probability of positive given happy is present in it. Okay. Of course, there are other words in it, but we are not given any information on it. So we have to rely on just the information that we are provided. So I'll just use the Bayes rule. I'll say probability of happy and positive is probability of happy given positive times positive, right? Probability of positive. Okay. Yeah, I'm just looking at the joint probability. Happy and positive is probability of happy given positive time probability of positive. Okay. And this I know probability of happy given positive is 0.25 times probability of positive is 0.4. Okay. Next, if I want to get the probability of positive given happy, I will divide this by probability of happy, which is 0.13 and whatever it is. It should be this one, I think. 0.77. 0.25 divided by 0.4 is 1. 1 divided by 1.3 should be 0.77.
Logically, 3% would have is negative and 10% is positive, so probably.
Yeah. Yeah. Okay. So they do get some explanation for this. Okay, now let's extend it. So the thing with in general with probabilities, likelihoods and posteriors, in general in machine learning, like I said, machine learning is just maximizing the likelihoods. Most of the time you will not see likelihoods, you will see log likelihoods. Okay, can somebody tell me why this is a good idea to have log likelihoods rather than likelihood? I'm sorry? The word the minus? Log likelihood is actually quite likely to be minus because it would be log of probabilities and probabilities are smaller than 1. Okay. So the thing is, in general, for more than one reason, we don't like multiplications. Okay, I'll give you one example. Okay, exactly. So I'll give you an example. Let's say that I give you that I have a sentence which has word from x1 to xt. These are some words, and I'm telling you that probability of all of xi's is between 0.1 and 0.2. I've calculated them, and these are their values. And I'm saying that t is, the sentence length is 1000 characters. Okay, 1000 words. And if I ask you what is the maximum probability that is possible? What is the maximum probability for this sentence? Probability of x1 to x. What is the maximum of this probability? Remember that individual word is maximum probability is 0.2. So if you take the maximum of all of them and multiply it, that will give you the maximum probability. So this would be 0.2 to the power. And you can see why this is a bad idea. Okay. That's one thing. Okay. Products can give you very small numbers in this case because the probabilities always be very small numbers if the sequence length is large. Okay. There is another more important problem than this. Okay. So let's say that you are doing this, you are calculating this probability based on some deep model that you have. Okay. And you have now some loss on the actual probability or the actual level y and the probability that you are assigning. Okay, probability that you are given to a sentence xt. Okay. So this loss function, of course, it would be some function of this probability that you are assigning to this sentence. Okay, and of course, this probability would be parameterized by the parameters of your network. Okay, so when you calculate the gradient, you will calculate the derivative of f with respect to p. Then after that, you will have to calculate the gradient or the derivative of your proposed network. Okay, and this thing I have mentioned that in all NLP, I just saw a tweet today from Andre Karpathy that now they're working on a diffusion-based language model, which would not be sequential, which would be producing the entire sentence. But up till now, we have sequential. It's one word at a time. So you will have this probability of xt, of sentence, I'm sorry, a vector. It's vector from x1 to x3. Let me write it like this. 1 to x3. This would be the product from I equal to 1 to t. And let me call it 2. Okay. This is probability of x1. This is probability of xi given x1 to I minus 1. So when you need to take the derivative of quantities which are products, you would have to apply a product. So you'd have to take these t minus 1 quantity and take the derivative of each one of these. This is horrendous. It will make your life miserable. Okay. Now let's take the log. Let's do the other side of the coin, the other option that we have available. The other option that we have available is, remember what was I doing originally in naive base? I was trying to find probability of x given positive and probability of x given negative. Okay. And I was saying that the cutoff, the threshold is 1. If it's above 1, then it's one thing. If it's below 1, then it's another thing. Now, any monotonic function that I put on it would just move the threshold. Nothing else would change. Okay? Log is monotonic. Log is always increasing. So I can apply log to it. And the only thing which would change is the threshold. Yes, so there are many advantages to it, but I'm giving you all the steps of what I'm trying to do. Okay, so I said that if it's greater than 1, then assign it positive, right? If I take log, so now this would become log of probability of x given positive. Okay. Minus log of probability of x given negative, and the threshold would become 0. Okay, and log is basically easy, the thing which was previously product. So remember, you had product of terms, right? So what was this probability of x given positive? This was in naive base. It was probability of xi given positive product from I equal to 1 to t. When you take the log of it, this would become summation from I equal to 1 to t, log of probability of xi. Similarly, for the so additions are easier to handle. They have less chance of blowing up. And as we would see in future lectures, when we start taking the gradients for it, it's also much more convenient to take the derivatives, the gradients, and taking a step in the negative gradient direction. Okay, so that's what we do. Let me show you in slides. Okay, so this is basically, they are defining a new quantity, which is so I basically wrote the log in one way. You can also write the log in another way, which what they're using. So what I did was, I had this log of probability of x. Let me write it 1 to t given positive divided by probability of x 1 to t given negative, and I distributed it between numerator and denominator, which is perfectly fine. You can also do it this way. You can say log of products I equal to 1 to t, probability of xi given positive divided by probability of xi given negative. Okay, and then rather than dividing it between numerator and denominator, you divide it over this fraction and sum of this fraction. So you write it as summation I equal to 1 to t log of probability of xi given positive divided by probability of xi given negative. That's what they're calling lambda. Okay. So you calculate all these lambdas, okay, which essentially is this quantity divided by this quantity log of it. This quantity divided by this quantity log of it. Okay, you get these lambdas, you add them up. If it's greater than 0, it's positive class. If it's less than 0, it's negative class. Okay. That's basically naive Bayes classifier. Okay. Everybody is with me? Any questions so far? Let's do a short example. I think I have one for this. See that all of us are on the same page. Maybe not on this one. Okay, the last thing that I want to do is I want to talk a little bit about data processing as well, because it's going to be an important component of your NLP journey. You might have some data which is proprietary data provided inside the ministry, generated inside the ministry, which you guys might want to process to remove the stop word, to remove the punctuation and these type of things, and creating like a clean data set from it. So for certain applications, like sentiment analysis, there might be words which are not useful. For example, to, be, am, these type of words, which are not particularly of interest to us, we call them stopping words. So let me show you. Okay. So these are called stop words. Okay. These are typically not super important. Punctuation is typically not super important. Remember, these are slightly classical techniques. In modern techniques, we don't remove them. But still, you might have certain applications where you, for example, you have data, you have something, some part of it in Arabic, some part of it in English, and you want to do something purely on Arabic, and you want to remove that English part. Or maybe you are in 911 dispatch, and the transcript that is being generated, there is some computer generated part in it and some real text, and you want to remove it. So you need to have the ability to clean your data as you want it. So though I will walk you guys through an example where you have some raw text and you clean it up, you create a nice dictionary for it, remove the words that you don't need, use the words that you're going to need. Okay, but traditionally there were techniques for removing stop words. There was also a technique for lowercasing is a standard thing. Typically, you would lowercase your data and go from there. And you also do stemming. So stemming is basically word with compounded ending. We remove their endings and we use just the base word. This has decreased the dictionary quite a lot. Yeah, and for applications like sentiment analysis and things like that, it's a good thing to do. Might not be a very good thing to do for language modeling, because in language modeling, you want to get these words. Okay. It does, of course, include its own problems. If you are removing good data from your data, then it would be problematic. But most certainly, in implications are like yours, where you have 911 data and some data is not, let's say, good for your application, you have to remove it. And it's good to be aware of some of the techniques to use for that. So, Noah, do you want to come to the front and give us an example for that? Thank you. Then what is the net of what What is the notebook called? Tokenization.
Solve the versions problem, right?
Sorry?
Solve
It is also.
تركز معي شوية بس سريع وسهل اللاب. اللاب الأول أخذنا TF-IDF فيكتورايزر، هي تسوي كل شيء لنا وتجهز لنا التكست صح؟ الحين إحنا راح نعرف زمان كيف كانوا يسووها يعني في البداية مرة. كل شيء كان مانيولي، البانكويشنز كانوا يشيلوها مانيولي، ستوب ووردز كانوا يشيلوها مانيولي. طبعا أول شيء أسوي import للميثودز libraries عفوا اللي أنا أحتاجها، والداتا سيت برضه نفسها IMDB. راح أسوي داونلود للداتا سيت حقتي. هذه المرة اخترنا بس الترين داتا عشان أسرع الوقت يعني، أو السبليت اخترت التريننج، وبرضه راح ترجع لي هي ايتريتر. أوكي بدأ هنا. طيب في ال NLP في المهم طيب وين راح؟ I don't know how to use Mac. ما أدري. It went to the old lab. طيب في ال NLP في كلمات كثيرة ما نحتاجها زي إز وذا أو آن، ما لها معنى يعني لما أحد يقول لي ذا طيب ذا إيش يعني ذا، ما أقدر أستخلص منها شيء مفيد. نفس الشيء علامات الترقيم، أنا ما الفاصلة ما تفيدني أحيانا، وعلامة التعجب ما تفيدني. فزمان إيش كانوا يسوون؟ كانوا يشيلها مانيولي يمشي على الدوكيمنت كامل. أحيانا والله الدوكيمنت كانت مرة كثيرة، فكان يمر عليها كلها ويسوي لها بري بروسيسنج، بعدين يبدأ يدخلها في الموديل. فأول شيء نسووه يشيل علامات الترقيم. كيف نسوي؟ ممكن نستخدم دالة اسمها make trans. أول شيء لها ثلاثة، ما أعرف شو اسمها صراحة، بس ثلاثة مدخلات. أول شيء مدخل إيش اللي نبغى نحذفه، اللي إيش بنخليه، وإيش الشيء اللي نسوي له ديليت بالكامل. فأنا هنا قلت إنه أحذف علامات الترقيم بالكامل وخلي بدالها فراغات، إنه الاستفهام خلي بدال فراغ، والنقطة بخلي بدالها فراغ، وهكذا. الماك ترانس بس تسوي التيبل هذا اللي حول ذا لذا، والترانسليت هي اللي تطبق هذا الشيء. فهذا الميثود بس تشيل العلامات الترقيم. بعدين الميثود اللي تحت هذا الستوب وورد. الستوب ووردز اللي هي زي الضمائر، الآ والآن والذا، الواز والوير والديد والدوينج، هذه الأشياء. فإحنا ليش استخدمنا ست؟ يعني لما استخدمناها لست، لأن الست فقط تقبل unique values. لو أنا مثلا كررت I مرتين راح يطلع لي ايرور، يقول لا I أصلا موجودة من أول، فخليها مرة واحدة فتسهل لي أصلا الشغل. طيب بعدين في هذا السطر هو تقريبا هو راح يمشي على كل الدوكيمنت، يبدأ يشيل في الستوب ووردز. إيش يقول؟ word in word text split. text split استخدمناها عشان نخلي الدوكيمنت حقي عبارة عن tokens، يعني مثلا كل كلمة تكون لوحدها. بعدين أنا راح أشيك هل هذه الكلمة موجودة هنا ولا لا. لو لا أسويها join، وخلي بينها فراغ. يعني مثلا خلينا نقول I love this movie، راح أحط I لوحدها يقارن هل I موجودة هنا ولا لا. أيوة موجودة، فما راح أحطها. مثلا love، هل راح أشوف إن هي موجودة؟ لا، فراح يسوي لها join. this موجودة، most likely موجودة يعني، راح يشيل this كمان. بعدين موفي بحصير love movie بس بعد ما طبقنا هذا الميثود. طيب بعدين هنا diff tokenize الفانكشن هذه مهمتها بس إنه بعد ما أنا سويت هذا البري بروسيسنج كله، مو صح إني أنا سويت جوين، فأنا بس أرجع أسوي له سبليتنج عشان الكلمات حقتي تكون لوحدها، مثلا زي لو تصير لوحدها ومو لوحدها. طيب اختصارا للوقت، أنا هنا خليت السامبلز راح أشتغل عليها 100 لأنه مشيت عليها كلها راح ياخذ مني وقت مرة كثير. أوكي بعدين قلت فول ريكورد الداتا سيت حقتنا تو ريكوردز. الريكورد الأول اللي هو الليبل، والريكورد الثاني اللي هو الريفيو. طيب فأنا ما أبغى الليبل أمشي عليه، الليبل أنا ما أسوي له بري بروسيسنج، البري بروسيسنج راح أسويه بس على الريفيو. عشان كذا قلت إنه أمشي على ريفيو واحد، عفوا ريكورد واحد اللي هو الريفيو حقتي. بعدين أنا بس أبغى أول 100، فهو هنا فعلا بس بيستخلص لي أول 100 ريفيو من الداتا سيت حقتي. طيب بعدين هنا أنا فعلا راح أبدأ أسوي البري بروسيسنج. طيب الفوكابلري اللي هي اليونيك ووردز اللي أنا عندي في الداتا سيت حقتي، الداتا سيت الحين عندي 100 ريفيو بس، أنا استخدمت ست لأني أبغى بس اليونيك، لو خليتها لست ممكن يكرر لي هي، أنا ما أبغى ذا الشيء. طيب الحين سويت فور لوب عشان أمشي على الميثود حقتي. أول شيء خليت التكست حقتي لور، لأن بايثون كيس سنسيتيف، this capital غير عن this small، لازم كلها أخليها نفس الشيء. بعدين راح أبدأ أشيل علامات الترقيم وأوديها البناء، بستدعي الميثود حقت علامات الترقيم. بعد ما أشيل علامات الترقيم بشيل السب ووردز، بعدين بسوي لها توكنايزيشن. طيب توكنايزيشن راح ترجع لي الميثود راح ترجع لي الكلمات في ليست، وممكن تكرر لي الكلمة لأنها ليست عادي، ممكن تقول موفي 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 3 مرات. فأنا لما أسوي أبديت للست هذه راح تخلي بس أول أكرنس للكلمة، مثلا موفي أول مرة خلاص خليها، ما راح أكررها مرة ثانية. وفي هذا السطر هنا TF IDF فيكتورايزر برضه تسوي لي هذا الشيء دايركتلي. الموديل ما يفهم الحروف، فأنا لازم أحوله أرقام. هنا هذا الشيء قاعد يصير، راح تمشي على كل كلمة، أول كلمة راح تعطيها 0، ثاني كلمة راح يعطيه 1، وهكذا لما تخلص كل الكلمات اللي عندي في الفوكابلري. هنا لما جيت طبعتها هذا اللي أوجد لي هي، مثلا أنا قلت له الريفيو رقم 10 أعتقد، أيوة أول 10 كلمات من الفوكابلري أعطيني هي وأرقامها. فقال مثلا definitions أعطاها 0، tales 1، وهكذا. طب هنا بس أبغى أشوف example كيف راح يمشي هذا البروسيس. أنا قلت له إن الإندكس اللي أنا أبغاه 10، يعني كأني أقول له الريفيو اللي أنا أبغاه الريفيو العاشر. فهنا أنا برضو بسوي نفس الشيء، بستدعي دالة علامات الترقيم، لازم أسويه لور عشان ما يلخبط لأنها كيس سنسيتيف يعني. راح أقول له إنه شيل علامات الترقيم، شيل الستوب ووردز، بعدين أسوي لها توكنايزيشن. وهنا أنا بسوي الأرقام، بعطي كل كلمة رقم. أيوه هنا مثلا هذا الريفيو العاشر كان كذا: it was great to see some of my favorite stars، وهكذا. بعدين زي ما انتم شايفين it was راحت كلها ونزل great بس، لأن it was كانت stop words. وشال to وخلى سي، وسم شالها وشال of my وخلى favorites، وهكذا. والفاصلة هنا شالها كمان ما خلى. هذا الثاني. بعدين لما جيت هنا، لما جاء قاعد يقارن في الأرقام، قال إنه أوكي great كانت الكلمة الرقم حقها 1373، هكذا راح يمشي على كل الكلمات اللي هنا. طيب طبعا هذا بس بري بروسيسنج، احنا لسه ما سوينا الموديل. هذا البروسيس ياخذ وقت مرة كبير، بالذات لو كانت أحيانا لغة ما نعرفها احنا، مثلا فجأة يقول واحد سوي لي اياها بالأسباني، ايش عرفنا ايش الأشياء بالأسباني مثلا. ومشكلتها كمان قرأت ناس مرة كثير إنه في الستوب ووردز في أشياء ما يكونوا حاطينها، فيروح يضطر يقرأ الستوب وورد كله كامل عشان بس أضيف مثلا كلمة واحدة. فالحين في عندنا ميثود لايبرري عفوا اسمها سبيسي، سهل لنا هذا الموضوع. سبيسي تستخدم موديلز عشان تسوي موضوع البري بروسيسنج حق الداتا سيت. فهني أنا الموديل اللي أبغاه اسمه English Core Web Small. Small اللي هو حجمه، في ميديوم وفي لارج. Small اختصارا للوقت يعني. التكست حقتي أنا راح أرسلها للموديل هذا اللي هو اسمه English Core Web Small. راح أرسل له، راح أحفظ كله في دوكيمنت واحد. طيب الآن أنا لما أستدعي هذا الموديل راح يرجع لي document object. طيب هذا الدوكيمنت object راح يمشي على كل كلمة عندي في الداتا سيت. راح أشوف إيش وضعها. لو كانت stop word راح أخلي هذا ال variable is stop true. لو كانت ما هي stop word راح أخليها false. فأنا هنا كأني أقول له في الستوب words شيل الستوب words أو شيل الكلمة هذه إذا كان الستوب word حقها true، خليها لو كان false. تمام. بعدين هنا أنا بسوي لها tokenization، إنه أخلي كل كلمة لوحدها عندي. فتوكن دوت تكست for token document، أيوة ترجع لي list of words يعني. أنا هنا بس سويت البري بروسيسنج. الحين أسوي الفوكابلري. الفوكابلري زي ما قلت راح يعطينا الوردز اللي عندي بس يونيك، ما راح يكرر لي هي مرة ثانية. فهنا أنا بستدعي remove stop words، الميثود اللي أنا سويته هنا عشان تشيل stop words. بعدين بسوي لها tokenization وأبديت للست عشان نضيف له كل الكلمات حقتي في الست. وهنا أنا بسوي الأرقام، كل كلمة بعطيها رقم. طيب. وهذا مثال إنه أنا أبغى أول 10 كلمات نفس الأوتبوت اللي كان فوق، بس إنه هنا أنا سويتها بأسطر أقل جهدا كانت. وبرضه هنا نفس الشيء، أنا قلت له أعطيني الإندكس 10 وشلت منه الستوب وورد، سويت له توكنايزيشن أعطاني هي كاملة. في شيء في سبيسي إنه حاليا صرنا نقدر ناخذ كونتكست من علامات التنصيص. يعني مثلا علامة السؤال هيفهم إنه أوكي هنا سأل شيء، بس بيس تعامل علامات الترقيم كشيء لوحده. يعني مثلا زي هنا الفاصلة خلتها توكن لوحدها. لو أنا استخدمت مثلا، في بعضهم زمان كانوا يستخدموا سبلت مشكلتها إنه خليها مع نفس الكلمة، مثلا جريت فاصلة، أنا هذا الشيء ما يفيدني أحيانا. فكمان هذا الشيء عن سبيسي إنها علامات الترقيم تعملها كتوكن لوحدها. أوكي. أيوة هنا قاعد يشرح عن سبيسي وكيف إنها تعامل علامات الترقيم لوحدها. يعني مثلا هنا لما استخدمت الموديل الأولى حقتي خلى هاي فاصلة. أيوة هنا الأبوستروفي هذه، ولكن هنا في سبيسي خلت كل علامة ترقيم لوحدها، عملتها كتوكن واحدة. وبس هذا اللاب. هل عندكم في سؤال؟
يمكن الداتا تحتاج كليننج قبل، لأنه بعد ما تستخدمها بسبيسي شوف في توكن غريبة. لو توكن من هذا اسمها ايش؟
وين هنا؟
الثالث يعني دوبيوس، كلمة دوبيوس بعدها بيها
وين شايف؟
لا definitions tells dubious.
والمثلين
اوكي طيب.
هذه ما كانت موجودة قبل.
اوكي
كان الأولى.
طيب اوكي ما انتبهت، شكرا.
هل كان في كليننج قبل ولا سبيس نسوي أي كليننج من الناحية هذه؟
صدقني ما ادري اصلا، توي انتبه لذا الشيء. هذا ايش؟
ممكن إضافات من سبيس.
يمكن ايوه لاحظت، تصدق اني ما ادري، تو انتبه لهذه. حتى انتبه كان اللي قبل كانت فيها نفس الشيء. ايوه من سبيس نفسها. ببحث عنها واقول لكم لاني توي ادري فعلا عن هذا الشيء. اوكي ملاحظة فنانة. حمدان. يا
So, I had to promote someone in the college.
I will leave 10 minutes early. I hope it's okay with you. So the break is from 12 to 12:30. We'll meet at 12:30, might be 5 minutes late, 12:35 sharp. We'll open the next lecture. Yeah, it's my target. So my target is to have like 2 sessions each day. This is the morning session, the afternoon session. Afternoon session would be a third one. Thank you.
في ناس من برا الهاوس يعني بيشوفون لنا ويسوون ديبلويمنت شركات هاوس عندهم شركات قال ذكر يوم قال لنا لا لا هم مزن قالوا انتم تسوون شركة مع اي كلاود كمبيوتر كومباني فهم يسوون يعني هم اللي يثبتون نفس اللي يعني يكون متخصص نفس اللي بتسويه
بس مدن شو يسوون؟ يعني يساعدون يعني
شيء في الاستراحة وهم يساعدونا في تثبيت برنامج هم يثبتون يعني على الكلاود موزن نفس اللي تسوي كاوس يعني كلام حسن يجيبون لنا خبراء في السكيورتي في الانفراستراكشر هذول يساعدون كان مكتوب انه كانوا كاتبين مينيمم MVP وبعدين حسن كان هم اللي يكون كل برودكت بعدين شالوا الشرط حق MVP كامل ما كتبوا في البرودكت ما أدري هل يوم أنا سويت ملاحظات إني كتبت إنه ترى ما شالوا MVP ما كتبوا في البرودكت فما أدري إذا رجعوا أدري على الأخطاء ممكن نتأكد من هذا الشيء هل يعني بيعطونا في البرودكت أو لا مين بس
خلاص واضح خرج له يعني بس هم عرض سلوك واضح
هذا كتير خمسة جيل كتير صح؟ عدد الناس يعني بيسوون خمسة وسبعة بس ترى حسب إن الهاوس عندهم شركات من حول العالم ناس من حول العالم يساعدون بس عندنا هذا النقاش عن هل بيكون كل برودكت ولا MVP
يقول إن شاء الله يقول إيه تمام نكمل ولا نقول لا
لازم نسوي اجتماع ثاني
شوف الموضوع مو موضوع في لازم شيء لازم شيء هي إن الجزء
أنا ودي نشتغل على الموضوع. أنا
لا لازم
لا مو طبعا
ايش صار مع صاحب؟ لازم تمام والله بس كذا ليش والله ناجح ما تحب الدوريات ولا حاجه بس ممكن على على طول
Hey guys, can we? People are relaxed, huh? Can you drop a message in the group? Dua. Dua.
قال لطيف انا زواج مصور في خير انا شيء لطيف ما سمعت
Okay, guys, so what are the other guys? Yeah. Yes, please. So can you guys see my screen on WhatsApp? Sorry, on Zoom?
Yes, yes.
It's not the code, right? It's the white screen. Okay, perfect. Okay, so let's talk about the okay. So far we have looked at the classical feature extraction techniques and naive ways. Now we are going to look at the holy grail, the main problem of language model, sorry, of NLP, which is language modeling. Okay, essentially to have models which can create realistic looking language. So what I want is, I want a probability distribution on language on text from which I can sample. Okay, that's what ChatGPT is. That's what Gemini is. That's what Cloud is. That's what all these large language models is. I want to do language modeling. Okay, of course, as always, the problem is that I don't have access to this distribution. Okay, I have access to samples from this distribution. Okay, so I have data. I have sentences in English language. Okay. which in this case is, I would say, text on the internet. And that's English text on the internet. So I have too many samples from this distribution. I don't have access to this distribution. How do I learn this distribution? What should I do? I'm sorry? Sampling distribution, but I don't have this distribution, right? I just have samples. How do I learn this distribution? So what I'm saying is that if I give you all the text on the internet in English, and I ask you to have a model, a machine learning model, which can look at this text and then learn to produce English. How? Okay, okay. So what our colleague is saying is essentially a key idea which I repeat over and over again is that all machine learning is maximum likelihood. Okay, let's try to do this. Let's create a parameterized model, okay, which will give me some probability on X. And what I will do is I'll just try to maximize this probability. Simple thing. So what I'm saying is I cannot access the model, the real probability model, but I can create a model which will produce the data that I have with high probability. Okay, that's the best that we can do. So now let's try to see how we will do it. Okay. So the way we would do it for languages that, of course, the first thing that we did was for a sentence X, we can write the how do I say it? The probability in terms of individual tokens. So using Bayes rule, I can write probability of the sentence as probability of first word multiplied by probability of second word given first word and so on. That's the first thing that I would do. So I can, for example, have probability theta of x1 times probability x2 given x1 times probability x3 given to x1 all the way to probability of xt given so is it okay if I write it like this? All the xt is less than, let me write it explicitly, I don't want there to be any confusion. I'm going to write it 1 to t minus 1. Okay. And this, by the way, is exact probability. Okay. So let me write it like this. Yeah. This is what I want to do. Okay. Now, a few challenges. Okay. First thing, let's say that I have some model. All of this is, by the way, parameterized by theta. Let's say I have a model which can do that, which can take a sentence of variable length and produce the next word. Let's say I have that. The question is, this seems like a supervised learning problem, right? You are giving input to a network and it's giving an output. But here I don't have any supervisory signal. I just have text from the internet. How do I use text from the internet to solve this quote unquote supervised learning problem? Yes. So this is something called self-supervised learning. Essentially, what I will do is I'll take sentence from the internet. Let's say NLP is the dominant area of research in AI. This is the sentence, one sentence from the internet. Okay. What I will do is I'll give to my model the word NLP and I'll ask it to predict is. Then I'll give my model NLP and is, and I'll ask it to predict the, and so on. So the good thing in this approach, in this self-supervised learning, is that I have virtually infinite data. I have large amount of data. Okay. Now the question is, how do we learn from this large amount of data? Okay. So what's the challenge? The challenge is, So far, what type of tools do we have that we have studied up till now? Are deep learning tools. Okay, and deep learning tools takes, at least the one that we have studied, takes a fixed sequenced input, a fixed length input. We tried to do it with feature or something like that, but now we're going to look at more general, more broader solutions. So, okay, so what can we do to fix our problem to be of a sequence of fixed length? So these are, you see, the sequence length here is 0. It doesn't take any input, gives an output. The sequence length here is 1. The sequence length here is 2. And the sequence length here is t minus 1. Now I have to convert it somehow to a sequence of fixed length. So I'll try by the statistical tools, the first tools which were used for this. So before the era of deep learning, like early 2000s, the autocomplete that we had on our phone, the grammar checks that we had on our phone, these were done by these classical statistical models. Okay, and let's see what these classical statistics model are. Okay, so the core idea for this is essentially they're trying to use some sort of Markov property. Okay, so Markov property says that given some history, okay, the next state would be independent of all the previous history. So think of it like this, like if you are playing a chess game and you have a policy for it, the move that you make would only depend on how your board looks right now. It doesn't depend on all the previous moves that you have done. This is a Markov process. Okay? The next step depends on only the current state, it doesn't depend on anything in the past. So what they said is that, can we use something like that? Can we say that the next word would only depend on the previous 2 words, or 1 word, or 5 words? Okay. These were the methods which come with. And rather surprisingly, by the way, this is the approach which seemed to be working best, because this is what transformers do. Transformers say that the next word depend on the previous 1024 or 20,000, whatever the context length is. Okay. So the first attempt at these methods were called n-grams. Okay, so let's start with the simplest form of n-grams, which is unigrams, which says that each word does not depend on anything. It just depends on itself. So how would you do it? How would you calculate? You are given a data. You have some data. You know how to construct a vocabulary from it. You will construct a vocabulary from it. How would you calculate the probability? You just simply look at the frequency of terms. You would look at frequency of each terms. Now, what you will do is you will have a distribution on words, you sample from it. Okay, so you will be sampling words. Most likely the words which are most common would appear quite a lot. Of course, we know that in language, words are not independent. Okay, there is context, words have some relation with previous words. So unigrams typically would not be very, let's say, well behaved, will not have very good outputs. What's the next step after the unigram? What can we do? Bigram. So we say each next word depends on the previous word only. We will say that probability of the word at time t depends on the word at time t minus 1 only. Okay. So this would become probability of our expression, this language model expression would become probability of x1 time probability of x2 given x1 time probability of x3 given x2 all the way till probability of xt given xt minus 1. Okay. Now, a question is, how would we calculate these? How would we calculate the probability of next word given previous words? Okay, we can calculate it through Bayes rule. Okay, you're right. But let's, of course, to use Bayes rule, we would have to first find the frequencies, right? How do we find the frequencies? What do we do?
We construct the vocabulary.
Okay. Okay, so you construct a vocabulary and you do the count. Okay, so you will have a vocabulary. Let's say some words. So I'll call them V1 to Vm. These are the words. You do their counts. You have counted them. So V1 is used 100 times. V2 is 200 times, and Vm is used maybe 5 times. You have that. How do you calculate probability of the next word given the previous word from it?
We should do combination, also the count of combination.
Okay.
Make it easier. So we'll have also the count of this word, given that the another token is before it, and do all the combination.
But isn't it too much counts? How are you going to keep track of it?
What's the probability of this one,
Mm.
given that we beat this one? Is disappeared.
Okay, okay. So the thing is, Muhammad's idea was correct. We just do it in a smart way. So what we do is we calculate a frequency table where we have from V1 to Vm, and we have V1 to Vm. Okay. So now what I start doing is that I start taking a pair of words in my language. Okay, so what was the original sentence? We had NLP is, what was the sentence? NLP is the dominant area of research in AI. This is the dominant area of research in AI. Okay. So what I'll do is I'll say that, hey, we have NLP and is in my data. So I'll see where I have NLP here and where I have is here. I'll add one here. Okay. Then I have is the, so I'll see where is here. I'll see where the is here, and I'll add plus one here. You can do that. You can quickly do it. You can parallelize it. It's nothing stopping you from parallelizing it across documents, right? So essentially, this is what you do. Okay, now let's say that you have this table filled up. It's basically joint frequency, the frequency of pairs occurring together. Now you have this. Okay. So what is each entry? This entry is the count of word is followed by the. Okay. This thing is the frequency of word, the count of, I'm sorry, or the frequency of NLP followed by S, and so on. You have all of these. But what do I need? I need the probability of is given NLP. How would I do that? How would I take the joint probability or the joint count and get the conditional probability from it?
So we divide the count by the total number, then we get the probability of NLP comma S. Then we will divide it by the second one. The probability of the second, which is the probability of S.
Okay.
Basically.
Okay. 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 So I would have a slightly different. I'm doing exactly the same thing, but I'm doing it in a slightly simpler manner. Okay. So remember what I'm interested in is probability of, let's say, probability of is when it's following NLP. Is it okay to say that this would be equal to the count of NLP when the second term is divided by the count of
All the pairs. It should be divided by the total number of pairs that we have out there.
Yeah, I know. So it's the total number of pairs. Basically, you go to, you will divide it here, total pairs, but you will also divide S with the total number of pairs. Okay. So it's essentially the same thing. It's basically you see when you see how many times the document has is, and then you see what is it followed by. Okay. If let's say is used 10 times in the document and 5 times it's followed by an then the probability of the given S is 0.5. Okay, but now we are doing it in an efficient manner. Okay, we are just creating this count matrix and then quickly extracting the probability values out of it. Everybody's with me? Okay, so essentially, once again, let me repeat the process. You create a matrix, all the vocabulary, all the words in your vocabulary, and you count their frequencies. Count the frequencies of co-occurrence. Okay, the followed by is and so on. Once you have these numbers, let's say that this is word at t-1, this is word at t. Okay. So let's say you are interested in probability of this word time t, give it this word at time t-1. So what you will do is you'll take this number divided by sum of this. So you'll take, no, it's 0 because wt-1 is here. We are finding the probability of wt given wt-1. So wt is in rows. Yeah. Okay. This is rows, this is columns. That would give you the probability of wt given wt-1. That's it. Okay. Now you have the probability of next word given a word at 20. Okay. There are, however, a few things which we skipped. Okay. So the first thing is if you look at my language model, all of these are in consistent format except for this. This is probability of x1. This is unigram probability, then followed by bigrams probability. Okay. Can I do something to make it consistent? Can I add something to my data to make it in a uniform format rather than doing two things where I calculate unigrams and bigrams both? Start of the sentence. Okay. So what I will do is I'll say that I have a special character which is start of the sentence, and all sentences start with it. So now what is the probability of the start of sentence? It's 1. And then after that you have bigrams. Okay. So now your vocabulary would be added by 1. Okay. And it would continue. There is another issue, however. And the issue is that if you look at it, you can continuously sample from this. So the sentences would go on and on and on and on and on. But of course, real life sentences do not go on and on and on. They finish at a certain point. So how do we fix for that? You will put a special character for the end of sentence as well. Okay. So I would say that I have another character which is end of sentence. Okay. And now this becomes vocabulary size time 2. That's it. So you take your data, you augment the special characters at the start and then you do the count, you create the frequency tables, you have now the distributions. Now you have actually created the first language model for yourself. You can create text. Okay? You can create English language. Okay, and this is, like I said, this autocompletes, early 2000 autocompletes, spell corrections, grammatical things. This is what they were using. Bigrams. They were going up till 5th gram, but it was n grams in general. Okay, because this I used Markov property in the simplest form. I said like, okay, the next word would depend on the previous word, but I don't have to restrict myself there. I can say that the next word would depend on the previous 2 words. Right? I can say that. I can say that the next word would depend on the previous 3 words, previous 4 words, previous 5 words, so on. What's the issue, however, with this approach? Yes. Okay. So if I'm doing bigram, the matrix is vocabulary size times vocabulary size. Okay. If I'm doing trigram, the matrix would be vocabulary size times vocabulary size times vocabulary size. Okay. If I'm doing 4 grams, it would be vocabulary size to the power 4, and so on. And this becomes bigger and bigger and bigger. Yeah. So typically, I think the maximum that they used to go to was like 5 gram to 7 gram, I think, if I'm not wrong, but not beyond that. Because it just becomes too complex. Okay. This is not, however, the only issue. What is the other issue with going with big n grams? Okay. N grams, let's say, n is greater than 6. What is another issue that that we would say?
Overfitting, maybe. Just memorize some of the sentences.
But overfitting is something which you can always solve with data, right? So let's say you have infinite data. What issues are there? Huh? Okay, so the thing is, the longer context that you take, the sparser this matrix will become. Okay, why? I'll give you an example. So let's say you're using 5 grams. Okay? So you're using 4 words of context. Okay. Now, of course, you are going to go over all combinations of your dictionary. Okay. So the probability of observing the word the is very low. Would you not find it? You would need exponentially more data to cover all combinations of data. Okay. So this matrix would become progressively sparser and sparser and sparser. Okay. And sparse matrices are typically we don't want it to be too sparse. We can of course do these Laplacian smoothing type of operation, but typically it becomes difficult. Okay, so large n grams will become sparse. Okay, so now we essentially have all the components. We know how to set it up, we know how to train it, and so on. Training n grams, by the way, is very simple. It's just you do frequency count. There aren't any trainable parameter. You get this matrix and things are set. Yeah. Okay, so let's look at this in detail and see if I'm missing anything. Okay, this is what I mentioned, that you can simplify it to probability of the joint pair divided by the probability of the preceding word. So the count of x and y divided by the count of x would give you the probability of y given x. Okay, similarly, trigram probabilities and so on. Let's take a few examples and let's see if we can do that. So what would be the probability of Mary likes cats, given that we have these bigrams and unigrams probability? You guys give it a try, see what we'll get.
This is the count, the frequency, right?
No, they're giving you probabilities. You're given probabilities. And I have to find the probability of this sentence. If somebody completes it, please let me know. Okay, so let me see. So this would be What are we looking for? We are looking for probability of Mary times probability of likes given Mary time probability of cats given likes. Okay, and let's try to fill in the value. Probability of Mary is 0.1. Probability of likes given Mary is 0.3. And probability of cats given likes is 0.1. So this should be 0.003.
Still the probability of cats giving Mary likes.
That would be bigrams. So we have in this case unigrams. Sorry, I'm sorry. This is bigrams. That would be probability of cats given Mary like would be trigrams. If you're using trigram, then you would use that. Here we are in this example using a bigram. Okay. Okay, let's look at the answers and see. It should be this one, and that's indeed the right answer. We have already seen some motivation for why we use the start token and the end token. Okay, let's look at another example and let's see what this says. So apply sequence probability approximation with bigram after adding start and end token. Okay, so can somebody tell me what that would be? Yeah, it's the same example. Mary likes cats. Yes. Okay, let's see. So probability of start is 1, so I don't need to worry about it. So what is probability of Mary given start? This is 0.2. What is the probability of Mary likes given Mary? This is 0.3. What is the probability of cats given likes? 0.1. And what is the probability of end sentence given cat? 0.6. This becomes 0.6 and 0.6, so 0.36 and 0, so 0.0036. Okay, let me see if that's correct. Should be correct. Okay. Yeah. So let me ask you guys another thing. Okay, we have done n-grams. Now I have a question. Using the setup that I have for n-grams, can I use deep learning tools to learn a language model? So what did we do in n-grams model? Essentially, in n-gram model, we said that probability of a sentence x is basically probability of let's say that I'm working with bigrams. Okay, so probability of x1 times probability of x2 given x1 times probability of x3 given x2 and so on. Okay. Probability of t given x1. If I that's of course approximately. If I'm given this, can I use deep learning tools to learn this language model rather than n-grams?
So that we count, so no.
No. Imagine that I'm not doing counting. Okay. Imagine that you have such a large amount of data that counts is not feasible. Can I use deep learning tools to learn something? Yeah. Oh, so what is your architecture? we don't need sequential thing because, I mean, like, of course, but you can use like a neural network or something like that. Why? Because now if you look at it, it is a fixed input, fixed output problem, right? The neural network takes in the previous word and gives you the next word. Okay, so it's a simple problem. You can use a neural network to learn from data is language model. It's a supervised learning problem.
So the number of labels that you have on will be covered with data.
Yes, it will be the vocabulary size, yes. Which, by the way, is all language model, the output probability is on the vocabulary size. So how would I do it? How would I create the data for this model? Essentially, what I would do is I will have any deep neural network that I like. Okay. It would take, for example, an input word. You can encode it any way that you like. Let's say I'm using one hot encoding. Okay. It will have a one hot encoding. And output would be a probability distribution on the language. Okay. It would be a probability distribution, probability of the first word in the vocabulary given X, let's say this is X, probability of the second word in the vocabulary given X, probability of the mth word in the vocabulary given X. And how will we get, what would be the ground truth? Let's say this is extreme. You have xt plus 1, you'll have a one hot vector for that. So you will have, let's say, so it would be all 0. It would be 1 at the location which corresponds to xt plus 1. And that's it. You have the data, you can print this neural network. Yes.
So neural network, the predictions will be the probabilities.
Yes. Good, it will give you.
Bayes theorem, is it deterministic? The value that we will get is the same always, right? The probability will be always the same result, but in the neural network, it's not deterministic, right?
Yeah. So I think what our colleague is saying is that if you apply n-gram, you have a fixed data. For n grams, you'll get the same values of probabilities every time. But this is a neural network. You'll start from some minima. You might get a different one. What would be the strength of this is that you can use it with very large amount of data. Okay. Particularly if you decide to use more than one word. Okay. Now, if you look at, we said that the, what is it? If you have more than 5 grams or 6 grams, n grams would be sparse, right? Because it's an exact count. This would not be sparse. Because even when you have binary classification, it doesn't give you 1 or 0 exactly in probability. It gives you a distribution over the numbers. So it would be easier to sample from this. And because it's a neural network, it would learn to do some natural interpolation between things as well. Okay. So for example, let's say that in the bigram data, it was generated in, the data was from US. Okay. And let's say in US, the typical type of fruits are apple, oranges, and these type of fruits that we are familiar with. We have a specific fruit in Pakistan, it's called chiku, okay, which might not be present in US. But now when you give it 4 words, okay, in n-gram, you will not find it. The probability for everything for this would be 0 because it's not in the table. These 4 words do not exist in that language corpus. But this neural network, because it does some natural interpolation, it might be able to figure out that chiku in the context of these 4 words is something similar to a fruit as apples and oranges are.
Just predict the final probability, it will not calculate the conditional probabilities.
No, yeah, okay. But again, what it's outputting we would interpret it as the conditional probability of the next word given the existing words. Okay. So now that you have, here I give it 1 word. How can we give it 2 words? Let's say you want to do a trigram. Okay, you want to you have a Markov process where the next word depends on the previous 2 words. How would you do it?
Features to contain, each feature would contain at least, at most 2 words. 1 word or each word or 2 words.
Okay, you can do multiple things. You can take, for example, the 2 words and concatenate them. Okay, the feature vectors, concatenate them. Okay, or you can have some sort of, so we need ordering as well, right? So you can, slightly tricky, but you can have, for example, a sequence of word and use some sort of projection into some space for it. So imagine that you get a vector which represents the previous words in the vocabulary. Okay, I'm sorry, the previous word to a word in your vocabulary index. So let's give an example. Let's say that I have apple juice contains high amount of sugar. Okay, and let's say you are doing 5 grams. You're using the previous 5 words. Okay, so these are the previous 4 words. I'm sorry, these are the previous 4 words. Okay, so now the question that I'm asking is, if I want to train neural network for it, how would I do it? Okay, the first one is, let's say this is 1,500 word in your vocabulary. Let's say this is 3,000 word in your vocabulary. Let's say this is 981 word in your vocabulary. Okay, and let's say this is let's say 6,000 word in your vocabulary. Okay, so you can, for example, construct something like this. 981, 6,000. This can be a vector which goes into your neural network, but I'm telling you it would be significantly hard to learn things from this because the information is very compressed. Or you can, for example, have a 1 hot encoder. This one has 1 at 1050. Okay. This one has a 1 at a 3,000 location, and so on. Concatenate these 4, feed it into a neural network.
It's fast.
It would be very sparse. Okay, or you might be able to do something like this: 1 vector. So 0, 0, 1, and then 0, 1, 0, 0, 1, and so on. So 1 at all the words location, but you also somehow provide the order. Okay, so the order you can, for example, provide it by having another 1 hot encoder, which is 1, 2, 3, 4. It tells you which word was the first one, which one was the second one, which one was the third one, and so on. Okay, so these are the things which you can explore. Okay, or you can have, like, for example, take this and have a shallow network, neural network, which learns some embedding from this to feed into a neural network. So the first, multiple things can be done. But what I'm telling you is that if you use Markov assumption, the problem becomes slightly well posed for using deep neural networks. Okay, and in fact, what you would see is that the state-of-the-art solution, transformers, essentially is a neural network with one additional change, that in neural network, the weights that you are learning, this is independent of the input. Okay, so the weight is, after you have trained your neural network is trained, right? It is getting some inputs. Each of these are multiplied with some weights. These weights are fixed after you have trained it, right? The thing in attention is that these weights are a function of the input as well. That's the only difference in transformers and a normal neural network. I'll come to it, but I just want to highlight this point for you. Okay. So essentially, we are taking a problem where we have variable length inputs, and we are saying that we would take some fixed context length This context list can be 2 or 3 or 4, as we had in n-grams or bigrams or trigrams. Or it can be 10,000, or it can be 30,000 or 60,000 tokens, as we have with modern transformer-based architectures. But idea is the same. Okay, everybody's with me? Any questions? Okay. So I want to do one more thing, which is I want to do the last thing for today. After that, I'll let you guys go. Is I want to write the full loss function for a data set. So I'll give you a data set, a large data set, and I would say that the next word is, let's say, dependent on the previous T words or N words, whatever it is. Okay, and I'll ask you to write a loss function for this, the full loss function for this, and then we will see how to calculate gradients for it and see if we can minimize it. So the setup is like this. You have some data. Okay. So data, I would say you have n sentences. Okay. Each sentence has the size of t. T is variable. For different sentence, it can be a different thing. Okay. So sentence length. Ti. So sentence length is Ti. Okay. And I would say that probability of the next word, W at time t, just depend on W at t minus 1. It's a bigraph. Okay. So first, let me write the probability of observing this data. Okay. Given a network or given any machine learning algorithm that you want to set up, parameterized by theta, which given a previous word predicts the next word, how do I write the likelihood of observing this data that I have given? Let's write the likelihood of a sentence, one sentence. Okay. So for one sentence, probability of observing xi, the ith sentence. Okay. What is it? We've already seen it, that this is probability of x1. I'll write I1 times probability of xi2 given xi1. I, by the way, is the sentence number, and the second number is the position of the word. Okay, first, second, third, fourth. Okay, times probability of xi3 given xi2, all the way till probability of xi t minus 1. This is the probability of a sentence. Okay. Now you have n sentences. Okay. Now, how do I incorporate all these n sentences together? Remember, we have a very nice property in our simplifying assumption that we use, which is the assumption of assuming that individual samples are IID. Okay, so they are independent and they are identically distributed. So how can I use the independence here? Okay, so if you have two events, probability of A and probability of B, and A and B are independent, then what would be the joint probability of A and B? Exactly. Okay, so this is probability of a sentence. What would be the probability of x1, x2, all the way till xn? The probability of all my data, what would it be? It would be the product of individual probabilities. So it would be summation from I equal to 1 to n, probability of xi. Okay. And I have the probability of each xi. Okay. So now at least I have managed to write the likelihood of my data. Okay. Now I want to maximize it. I want to maximize this likelihood. As I've mentioned multiple times, that machine learning is just maximization of the observed data. It's just maximum likelihood. So I want to maximize this quantity now. Okay. As I've mentioned, for maximization, you would need to take gradients. Gradients of products are tricky. Okay. What can I do? I can take any monotonic function, and optimization of monotonic function do not change the minimum. Okay. So any function which is monotonic, if you apply it to a function and then look for the minimas, the point where the minimas is would not change. Okay, monotonically increasing it is. So if I take log, it does not change the location of the minima. Of course, it changes the value of the minima, but the value of the minima is not important to me. What is important for me is the parameters. I'm looking for the argument theta, which gives me the minimum. So rather than working with likelihoods, I would work with log likelihood. So I have probability theta from x1 to xn. Okay, this is product from I equal to 1 to n. And as I mentioned, because I'm interested in the minima, the point where the minima exists, not the value of the minima, I can take log on both sides. So rather than minimizing this objective, I will minimize the log likelihood. And under the log, this would become summation. Okay. You would typically find that we, rather than looking at the sum of the likelihood, we kind of normalize it in somehow with a constant, but it's unimportant. This is perfectly fine. Okay. So now we have the value of probability theta of any xi. We have that. Okay. Can we replace it here? So I have summation I equal to 1 to n. What is the probability of xi? The probability of a sentence is this. Let me replace this value here. So this is log of probability of xi1 times probability of xi2 given xi1 times probability of xi3 given xi2 and so on, all the way till probability of xi t given xi t minus 1. Okay. Again, I have log. So under the log, I can convert it into a summation. So this would become summation I equal to 1 to n. Okay. Log of probability of xi1. Okay. Plus summation I equal to 2 to t. Log of probability of x it given xi t minus 1. And that's it. Okay. That's what we typically do. Now, what you would do is if you have the start token and end token, then you don't need to worry to carry this individually, and it just becomes a double summation. So what you would do is you would sample a random sentence from your data, look at the previous, in this case, one word, give the one word to the neural network and ask it to predict the next word. Keep on doing it, and that's it. Okay. That's what we do in all language models, starting from the very simple one to the very advanced one. Okay. Typically, this was a maximization problem. Okay. If I need to find the argument of a maxima here, what if I put a negative sign? It would be a minima. And if I put a negative sign, let me just simplify it and rewrite it a little bit. if I do summation I equal to 1 to n, okay, summation t equal to 2 to capital T, okay, with a negative sign, log of probability of xi t given xi t minus 1. Does this look familiar? Should look like a cross entropy. Okay, that's essentially it. If I write it in exact cross entropy form, this would be summation I equal to 1 to n, summation t equal to 2 to t, summation c equal to 1 to c, indicator function of the class, which in this case is class is xi t, probability of c given xi t minus 1. Okay, minus c. That's it. So now we see how we take this very complex problem and through a series of operation brought it down to something that we understand very well. Just setting up a neural network, giving it some input, looking at the output, setting up a cross entropy loss on top of it, and minimizing it. That's it. Okay. So I'm hoping at least the high level idea of what language modeling does is very clear to us. Okay. Everybody is with me? Yes. Of course.
Why we put the first term I equal to 1 to the n? Isn't it only could happen once I equal to 1? I mean, isn't it a replacement for the log of the probability of x, the I1 only?
No. So I'm expecting you're talking about this sum, like why is it from 1 to n, right? Because you have n sentences in your data set, you have n documents, you don't have just one sentence. Okay, so for each sentence, you have to find the log likelihood of how likely the sentence is and add it, because the sentence are IID, okay, which means that their log likelihoods can be added. Okay, so the first summation is on the, let me write it like this. This summation is on sentences, okay, or more accurately, you can call it documents. This can be separate documents. Okay. This summation is on words in the document. And this summation is on vocabulary. Yes. On your vocabulary. Okay. So now when we practically implement it, because remember, this is the full loss. Okay. We would have to calculate the gradient of the full loss, and this can be massive. So what do? We do stochastic gradient descent. You will randomly select some chunks of data. Okay. Feed in the previous words, ask it to predict the next word, take the cross entropy loss and minimize it. That's it. That's what we do when you would fine tune a language model. This is what we do. Okay, supervised fine tuning. This is what we would do. Okay. Any questions? How is the first lesson for NLP? I hope it was not too dense. It's like easy to digest and swallow. And okay. Oh, this is lots of math. Wow. I'm surprised. Okay. Okay, but this is the most math that we would do in this class. We're not going to do anything more. Well, we will do some math for reinforcement learning with human feedback. That's one lecture.
We have the TSD of math.
No, math.
Is that lecture in Ramadan or before?
It's in Ramadan. It's going to be last lecture or the second last lecture. But the good thing is we are recording it. So you'll have I'll give you the recording. You can come back to these topics afterwards and look into it. Okay. Dora, Dua. Do you want to show the n-grams example today or? Okay, halas, we'll do it tomorrow morning. Okay.
Thank you.
Good luck and see you guys tomorrow, inshallah. Okay. Assalamu alaikum.
What we did like application.
Yeah.
I think it's starting now. I think it's in the second March.
Hmm.
Do you think I should go forward with the application?
Go forward. Go forward with it.
Okay.
And put me as one of your recommender. I would give you a recommendation. And what you need